like TV from other dimensions has a somewhat looser feel to it.
Yeah, it's got an almost improvisational tone.
Hey everybody! So I might be getting the green screen here in a few days, but for right now you just got the fun blue background, but so good to see everyone. A bunch of you are now moderators in the chat. If you can hear and see me clearly, say hey in the chat, and we're going to do something special right here. So if you can hear and see me, I want you to say hey in the chat, but I want you to do the following. I want you to write an @ symbol. I can't draw an @ symbol. People are saying hey in the chat, that's awesome. So I want you to do an @ symbol, and I want you to say hey at someone. Just say hey to someone. Say hey to like Luke or Julian or Miles or Lindsay or Yo-Yo. Say hey to someone in the chat. So if you see someone in the chat, I want you to say hey to them, and I want you to use the @ symbol, and you'll see what happens. So when you put an @ it actually highlights their name. So it's really easy to see if you're talking to someone right here that you just put the @ symbol and it goes right to them. So boom, I see people saying hey to Madeline, Hannah, Julian, Avery, Miles. All these people saying hey to everyone in the chat. But it's really easy to say hey to people. Got my orange juice. But really easy to say hey to everybody. And oh, sorry if Streamlabs, I have no idea. So you notice, and the mods probably saw that. Let me go here. Who was... So sometimes Streamlabs can be a little picky. And Streamlabs is what I have controlling the chat. Like, so someone can't come in here and say like complete craziness, but stay hydrated, you bet. Orange juice, water, all that good stuff. So thank you very much, Avery. Good advice right there. Stay hydrated, wash your hands, stay healthy. And so with this right here, I don't think anyone used foul language. Streamlabs is just like the thing I have on. I don't see where that happened. Streamlabs, you need to calm down. Streamlabs is like an auto moderator. It's like Nightbot if you've ever been in chat rooms. But so if you are a moderator, which I've made tons of people moderators, like every name I see that I know I've seen before, I'm like, you're a mod, you're a mod. So sorry if I didn't make you a mod, but I'm literally clicking through as many names as I can see right here, adding moderators. So if your name is blue, you're a moderator. If I didn't make you a moderator and you have a name I like, if you're a name like that I don't recognize, like if you're like, we have one of our favorite moderators is Calzone Tyrone. And we love him. He's from New York. He came into a Kahoot last semester, and he was just a great guy. So we made him a moderator. And if you're a mod, let's say someone were to come in the chat right now and just start saying craziness. Like if they were just like bugging us and they were like, oh, this guy's stupid. Why is he teaching on YouTube? We can literally click timeout on them. Now don't do that to anyone. So don't don't just click on random people and time them out if you're a moderator. We only use the mod powers if we get trolls in here, which we've dealt with them so well. It's random, but like maybe 1 in every 5 public streams we get a troll. And they come in, they might say something really stupid. And then generally you just don't react to them. You just click on them as a moderator and you go to timeout and someone probably beats you to it and you're like, oh, I wanted to time them out. And you can hide them on the channel, which they won't see that they're hidden. They'll type and it'll look to them like they're typing. It's so great because they'll be like, oh, I'm saying all these mean things to them. But no one will be able to see what they're typing. Like, I think we can't even see it. I think I can't even see it once they're hidden on the channel. They're completely, so we could have like 10 trolls in here right now that we've hidden, and they could be like, I'm making fun of this guy. These people are ignoring me, I'm totally bugging them. But so if we do get a troll, the first thing we do is we just block them on the channel. Now, once again, people might come in here and say something like, hey, what's going on? Don't block them. We random people who are here to just like see and learn and find out what we're doing. That's kind of cool. We like that. So we don't want to just put time out people who are just here to say hey. So what's up? I love it, Jake. All these people in the chat. So if you have questions, let's do this right now. Let's start. I haven't seen many of you in a while. My gosh, it's been like half a month. So I want people right now to tag me with a question because we do have the test coming up here. And so I want you to tag me right now with a question in the chat. This is a very interactive class. So I want you to tag me with questions. I'm going to get the notes pulled up here. But I want you to tag me, Stat201. I'm Stat201. So I want you to tag me with a question in the chat. So give your question. What will be covered on the exam? The exam will cover all the material on test 2 exam. You guys are cracking me up in the chat. So one of the best things you can do, here, I'll bring it down here. Let me show you guys. I just added in today, so I'm going to go through every one of these questions and we'll start today's lecture. But great, I see some great questions. I've added in a new tab, and so let me bring this down here. So here is the new tab on Canvas. And if you notice, I'll be posting the links for lectures right here. So the material on the exam is everything right here. So when you're looking to review, there will not be the central limit theorem on the test. Great question, Lauren, right there. So this is the material. Everything covered in these lectures is on the exam. So does that make sense to everybody right here? That this is the material you'll need to know: randomness, decision trees, sampling methods, probability, sampling distribution of the sample proportion, and then we do have confidence intervals. So it doesn't say confidence intervals on there, but that is covered. I should change the name of that video, but confidence intervals is on there too. So that is everything on the exam, and lots of great questions here. Are we review today? We're going to learn new material. So you should have watched the video I posted from last time. I posted a video for everyone to go over, and we are going to cover new material today. When will the test be on Canvas? We're going to release it Sunday night. So Sunday night, the test will be released on Canvas. You'll have Monday and Tuesday to take it. Can you help with number 4 on the homework? I might have done that yesterday. So we did some live streaming yesterday. Send me an email about it, Riley, and maybe I already did that one. What will be the format of the test? Lots of multiple choice, lots of true falses, and some calculations of it. So there'll be some calculations of it. And so we'll do all that right there with all the tests right there. And can you help with number 4 on the homework? There we go. Will chapter 14? Chapter 14 will not be on the exam. In your opinion, the hardest concept for exam 2, it's probably, let's go over here. The hardest concept for exam 2, boom, right there. Sampling distribution of the sample proportion, that one gets people a lot. So I think that one really gets people. Sampling methods are just going to be simply sampling methods are pretty much just memorization. A lot of questions. When will the tests, what do you think we'll struggle with the most? Probably sampling distribution of sample proportion. That one's all formulas. Are the last 2 quizzes open till Sunday, and last quiz and homework? The last 2 quizzes are open till Sunday, and do them to get a bunch of points because we're going to average that with your test. Will the exam still be a mix? Yep, there won't be fill in the blank. It will mostly be multiple choice, like numeric answer and true falses. No short answers. Do we get to use paper during the test? Yep, you can have scratch sheet of paper to work on, and you'll just show your paper. If you can't print the formula sheet, and I think I still have that up, I went through the whole formula sheet last night, so I'll show that here in a moment. Since the exam requires a calculator, I know the response requires you keep your eyes on the screen. Don't worry, we only really... Well, I say don't worry, please don't cheat with Respondus. But Respondus, I think, has a calculator you can use, a built-in calculator, and we won't be using advanced functions. So I think it has everything you need for that. You can still use the TIs. Just, I say this and I mean this. We really only move forward with cheating when we really think someone cheated. So just please don't cheat. We're trying to be, every time I move forward with an accusation of cheating, I'd say I'm 99.99999% certain someone cheated. And I've only let one person off the hook, and it was early on in my teaching career, and I feel bad about it still because I was so certain they cheated. And if I could go back in time, see, now I'm like, I don't know, maybe I made the right choice. But I move forward very rarely with cheating accusations. So realize if you're not cheating, we're probably not going to do anything. Just don't do anything you shouldn't do during a test. Don't leave the room. Don't have someone talking to you. Don't have books open. You have to do a full room scan. But if you show your calculator, show your table, show your calculator. And, if you're this is my calculator, this is my table, open up your calculator, show everything. So that way you're not pulling out a sheet of paper. Don't do anything that could be considered cheating. And so the study guides, great questions right there. We've got the review videos still up right here. And all the review material is still the same. And we're going to be posting a practice test. When the exam and the quizzes are averaged together, are the drops? Yep, John is right. The drop will be included. This will be in a lockdown browser also. Will the test close on Tuesday? The test will close Tuesday night. That is true. Is chapter 14 due tonight? Nope, it should be moved. Did I only move it for one class? If I didn't move it for you guys, I'm sorry. I'll move it if not. I thought I moved it for both classes. Can I get a confirmation in the chat right now? Did I move chapter 14 till Tuesday of next week? And so I might move it till Wednesday even, because Tuesday's the night of the test. Are the quizzes you're referring to the ones on my Pearson? Yes, the quizzes on my Pearson. It hasn't been moved yet? Let me move it right now. Sorry, I must have moved it for the other class. That's the joy of having two classes. So let me move it for you guys also. Not moved. No wonder. I was like, I thought I moved it. So the emails stopped coming in as much, being like, hey, can you move it? And I agree. We should move it. So let's move it right here. And so chapter 14, yes, it's still on this date. Okay. So let's move it. Settings for class. Thank you, everyone, for the reminder on this. Good questions. As I always like to say, feel free to ask, because when you ask, then it gets done. We're going to put it to Wednesday. Now, I wouldn't wait till Wednesday. There we go. Save and assign. So that is, I just moved one of them. And let's move the other one now. So now the other one. And I might reorganize these a little bit here. Now the other one, what does it not like about that? That was weird. And now the other one is moved. Do you say there will be a new review test? If so, yeah, we're going to post a practice test, Walker. Great question. So this should be moved now. And I might even try to do a Kahoot this weekend. So if you guys want, we might do like a Kahoot on like Saturday or something like that. Would you guys want, or maybe Friday, maybe tomorrow night we'll do a Kahoot. How does that sound for everybody? Tomorrow night Kahoot. We can actually do the exam 2 Kahoot now. Who knows? Yes, Kahoot. Avery says yes, Kahoot. Okay, we'll try to do tomorrow night. Is there going to be adjustments to the grading? Yeah, we're going to be as fair as humanly possible. So remember, please do the quizzes. Do the quizzes. And extra credit is worth now more than ever. So extra credit is so important to your grade. Because when it comes to extra credit, I can pull your grade up to 2 points. That's the system I've always used. So when you see me asking questions in chat, you need to be responding like this. I can see everyone's responses right now. I can see Rachel, Tyzone, Campbell, Haley, Wilson. All these answers. Are all the Unit 2 quizzes reopened, or just the last two? Just the last two, and that's a good portion of them, because I think there's only like 5 or 6, and one is dropped. So this is a great opportunity to get a really high quiz grade. And so we even put some extra attempts on it. I think there should be 7 attempts on them total. So with the extra attempts, with all of that right there, please do the quizzes. Please get as high a possible grade. Learn the material. It's some of the tougher material. And if you get it down, if you make a high quiz grade, it'll definitely help out your grade. And then we'll set up a Kahoot for tomorrow. So join in, take part in the Kahoot, and we'll have some fun. Any other last questions? We got a good kind of 15-minute start to class, get everyone oriented with the class and seeing what's going on. Can you go over how the test will be graded again? Let's hear. The test will be graded just kind of mechanically through Canvas, through Canvas Respondus. Oh, T-on. Is that, so am I saying it right now? T-on. So the test will be graded through Canvas, and that's how it'll be graded. And then I've still got the test in my office. I need to go down there. Sorry, everyone's like quarantined. So we should know the people who took the test in the morning. And sorry, it's kind of been a kind of like figuring it out as we go type thing. I think everyone kind of knows that. But if you are, read over if you want to try to do other options or stuff like that. But it's really kind of limited on the options now. How office hours going to work? We'll be live on YouTube. So Tion is right there. We'll be live on YouTube. If you want kind of more private office hours to talk individually, I can set up a Zoom meeting and we can meet that way. But generally, I want to do it as many public office hours as I can to answer all these questions so everyone can have access. I think it's a really great way to kind of be talking to as many people as possible. There we go. Is what we are learning today it's on the next test. Avery, it'll be on the next test. You also only have to make a 95 to get your sticker. You were right. How will the point system work online? You still answer the questions. If I say answer a question, you get the points. You get the points. So I'll keep throwing out points. Today's material will be on the next test. What time is the Kahoot going to be tomorrow? What time do you guys think we should do it tomorrow? We could do a noon Kahoot because I'm doing a thing at 10 for my other class, and then I could do the Kahoot after. We could do like a noon Kahoot. There you go. Is Canvas going to... I think so. I think it'll grade it immediately, and then we won't show you the results till maybe Tuesday night. So I think that's our plan for it, is it'll grade it immediately, and you'll know your score. But do remember this. Take a deep breath. Everyone just take a deep breath. And I'll send out information about the Kahoot. I'll send out all the info. People are saying noon is great. Awesome. And it'll be recorded, so you can watch it afterwards, and we'll have some fun. So, and then somehow we'll give prizes out somehow. And remember, we'll be recorded if you can't do it. But maybe we could do like a vote or something. Who knows? This is the biggest thing with the test. Let me go over, and this is what I talked about yesterday also. I also want to point out yesterday I did a whole video. Where is it? Yesterday I did a whole video going over the formula sheet. So here is the formula sheet for exam 2, and it'll be recorded and you can view it afterwards. But I did a whole video going over all of the formulas on the exam sheet. So yesterday I did, I could do a poll, yeah. I think, can I do it? Dang it, I don't have Streamlabs set up to do polls. Wait, give me 2 seconds. There is a way to do it. I'm not going to know how to do it this quickly. I don't know if you can do them in... I have to have Streamlabs pulled up. I'll need to pull it up. Okay, let me try this. Okay. Give me 2 seconds on this. I'm going to try something interesting right here. Wait. Okay. Let me try doing a live poll. If this works, this will be amazing. Dashboard. Okay, 2 seconds. Hopefully I don't... This is probably a very bad idea too. Oh, okay, something's happening. The assignment due tonight has changed. Awesome. Okay, so we're going to try to do a live poll right here. Oh, there's like a university thing? Oh no, did you have to go prime right here? So, CloudBot, polls. Okay, we got something right here. Okay. Okay. It says pick an option, but I don't forget to mod. It should be mod. Poll opened. I don't think it worked. We might just... Wait, a poll has opened. Okay, wait. Okay, don't vote yet. Do not vote yet, or else you will mess up the voting. I did open it up. Okay, wow, so I can do polling now. So, okay, you want to write hashtag, or you want to write exclamation vote 1 for noon and exclamation vote 2 for 2 p.m. So noon is exclamation vote 1 and exclamation vote 2 is 2 p.m. So that should do it. Give it a shot here. I'll see if the votes start coming in. I think you have to do a space and it has to be lowercase. Oh, no, that worked. That might have worked. And it might only count your vote once. But the way people are doing it, like John did it correctly, I think. Tiffany did it correctly. I do see a vote came in. It already shows. But yeah, let's let this... Oh, wait. Oh, wow. This is so cool. Yeah. Keep doing it. I think you can only vote once. Yeah, so you do, as people are doing right there, and use the lowercase v. I think you have to use a lowercase v. It might capture both of them, but use the lowercase v. So I think that's a lowercase v. Okay, so it looks like, and so yeah, lowercase v. Great job. Sarah's doing it correctly right there, and so is Lauren. It looks like noon is winning out. And there's ways I can show this on stream, so everyone can bet. I'm going to start working on this right here. It's starting to get pretty even. Someone's going to vote 3 for just the fun of it. but I can see the voting going on, which is so cool. So you want to use exclamation vote and then 1 or 2, just like people are doing right there. And so I'll take a look at this right. Oh, it's getting so close. No. Put a space. Yep. So you want to do a space. If you notice the way it has it right there, it's exclamation vote 1 and exclamation space vote 2. And I think you can only vote once. Like, it won't let people vote twice. So if you just make sure your vote was counted, it's literally almost 50-50. No. And there's ways I can show this on stream. So I'll keep, the more I'm streaming, the more I'll try to update this. Oh, now 2 p.m. is winning. So now 2 p.m. is winning. Okay, so it looks like we're going for 2 p.m. now. Unless we'll give this another 10 seconds right here. And here, I'll just finish off talking about this. Let me just talk about the formula sheet while you finish voting on this. So cool, we can get voting in the background now. And we'll use this a lot. I might just do option 1, 2, or 3 sometimes, but don't pick option 3 right now. So what we have going on right here is the formula sheet, and I did a ton of stuff over this yesterday. So we've got some really great videos coming out reviewing the formula sheet. We're going to do a Kahoot, and we're going to review concepts. So if you have any questions, feel free to ask. And it looks like by a small, narrow margin, I will show you who won. By a very small, narrow margin, 2 p.m. won. If you voted, you get 50,000 points. Yes, I mean that, 50,000 right here if you voted. Now people are going to start voting right now. But if you voted, you participated in this, helping us figure out. But we'll do 2 p.m. So I'll send out reminders for this. This will be recorded, but we will do 2 p.m. tomorrow. So you'll see a live video. We'll be doing a live Kahoot, and we'll do the 2 p.m. So 2 p.m. it is. It won the votes, and that's the way it goes. So many random phone. Like, that one's a random number. So last one's not, though. So this right here, we got it at 2 p.m. And so let's start talking about material now. Let's hop in here to the lecture material. So I'm going to pull up the slides. And let's get to new material today. I don't think I counted the one with the capital V's. So make sure when you vote, you have to use the lowercase v to vote. And so I'm kind of new to it too. That's fantastic. So I'm new to it too, and I don't know if it counted the capital V's, but I know in the way it showed me it had the lowercase v's. So I would think put a lowercase v in it to make sure it works. I do not know for certain there. So we are going to hop in to some new notes. Let me download these notes. I gotta look up here on my screen. And here comes the PowerPoints. Okay, cool. We'll make this nice and big so everyone can see. I need to enable editing. And let's start talking about it. Now, here's a huge thing. Please remember that on Tuesday, I posted a lecture for everyone to watch. So please watch that lecture. Please, please, please watch the lecture from Tuesday. It has material you need to know. Also, on yesterday, we did some office hours where we covered some key concepts. So anytime you have questions throughout today's lecture, remember this is interactive. 10,000 points if you say something right now. Who's listening? 10,000 points. You just got to say anything. You just got to be like, hey, what's up? So you need to be interactive, be here, be watching, be interacting, and be at your computer. Me, Sarah, you get 100,000 for being first right here. So 10,000. How many people we got live? Oh, yes, that's what I like seeing. 100,000. Why not everybody? Yes, like Lucas said something right there. So exactly. This is what I want to see. I want to see people who are live and interacting. That's what we got going on. Okay, here we go. Let's start talking about some new material. So chapter 14, confidence rules about the mean. Now, here's the biggest thing you should know. Oh, let me close the poll. That'd be a good idea. Streamlabs, close poll. Okay, complete poll. There we go. Okay, wow. I'll take a look at those options later, and it looks like that might be very helpful. There we go. 2 was the most with the 50. Oh, it actually shows you guys, so you guys can know I'm not, 2 is the most voted option. That's awesome. Okay. You're welcome, Lindsay. I like this format a lot. I like that I can see what you guys are saying. If you talk to me, I talk to you. That's the way it works. So we got a lot of cool features in this right now. Awesome. And let's continue on right here. Confidence intervals for the mean. Now, what you should know is you already have done confidence intervals. You've already done things like p hat plus or minus z star, and then we have square root, and then we have p hat q hat over n. We've already been doing this. Not like we've literally done it, but we've already been doing this to a certain degree. But watch this. Today, we bring out Space Pen. It's the best pen there is. And we are going to write y bar plus or minus t. What? N minus 1 is the degrees of freedom. And then s over square root of n. Now I'm going to highlight some stuff here as we talk about this. I want people to tell me, in the first interval we've done, what were we using to estimate it? Oh, no, thank you very much. Yeah, we've helped out a lot of people, and I hope your online classes are going well, and I hope you guys are enjoying this. Thank you, Luke and Lindsay, for giving some positivity. In the first interval we did for class, what were we estimating? You can say, yes, Sean, you got it right there. It used the sample proportion. Remember your notation. You should have notation down in the back of your notebook. If you don't have your notebook beside you, I tell my online class all the time, have your notebook out, have your pen out. And we previously did the sample proportion. And then after the sample proportion, we have the margin of error, which is everything after the plus or minus. And then we have a z. Why is a star on the z? Why do we put a star on the z? Can anyone tell me 10,000 points? Why is there a star on the z? And what does the z tell us? Why is there a star on the z? And what does the z tell us? What is going on? Tion, 10,000 points. But keep answering. I like the answer. What does the z tell us? And what is the point of z? What does the z tell us? And what is the point of z? Confidence interval, it tells us the confidence level you are right. And what does the star mean? The star means you choose it. Alexandria, 10,000 points right there. Great answer. The star means you get to pick it. It means like you can pick your confidence level. So if it's like 95, it's 1.96. If it's 80, it's 1.2818. So the star means you get to pick it. So we know what the z means. It's the confidence, like what tells us. Not quite the null hypothesis yet. We get into that. Still 10,000 points. Great answer. And we have right here p hat, which is the sample proportion again, q hat, which is the complement, if p hat is 0.8, q hat is 0.2, and then we have here the sample size. So we have all of this information right here. We have p hat, the sample proportion, q hat, the complement of it, remember just 1 minus p hat, and then n. Let's look at this just briefly here. We're not going to teach the whole chapter. But today, we're going to make a confidence interval using what? What is that right there? We're going to make a confidence interval today using the what? Today, we will make a confidence interval using the sample mean. Sarah, 10,000 points. And Walker, you are right. That is the sample mean. Yes, y bar, the sample mean, which means this is a confidence interval made from the sample mean. This is a keynote you should have about today's lecture. This is a confidence interval made from the sample mean to estimate the what? This is a confidence interval made. Stephen, don't worry, 10,000 points. Love all the answers. Confidence interval made from the sample mean to estimate the what? A confidence interval made from the sample mean. Yes, Sarah, 10,000, you are correct. Population mean or true mean. So remember, it's a confidence interval made from the sample mean to estimate the true mean. And just like previously, we made a confidence interval from the sample proportion to estimate the true proportion. Don't worry, Walker, I'm still throwing you 10,000. So these keywords that everyone's hearing before this is that the one I've highlighted now is a confidence interval made from the sample proportion to estimate the true proportion. Let's give an example about that. You guys know I love Taco Bell. So, man, I miss Taco Bell. Let's say we want to find out what percent of students like Taco Bell. Well, you'd go out and talk to 100 students, and maybe 70 out of the 100, 70% like Taco Bell. That would be your estimate of the truth, and from that, you would make an interval to estimate the true proportion of students who like Taco Bell. Does everyone see we get an estimate that 70% of students like Taco Bell, and from that, we'd use it to estimate the true proportion of students who like Taco Bell? So if you notice the question, it's categorical there. But today's, it should be 100%. I agree, Luke. 10,000 points, Luke. So today we are doing y bar as we start to get into the notes here. And today would be a question like, what is the height of UT students? There we go, Uber Eats, Taco Bell. What is the height of UT students? And heights, 10,000 points, Carson. Heights would be a quantitative question. So it would be something like, if we think of theoretical questions for today, we would have like, we go out and talk to 100 UT students and found an average height of 5'8". And so what is the true height of all UT students? So the true average height of all UT students. So we are trying to figure out the true average from a sample average. Does that make sense? The true mean from a sample mean. What is our best guess of the true mean? Someone's got to say it in chat for 100,000 points. We got a button for this. When I throw out those 100,000 points, we got to hit that button. So the question is, when we are trying to, I forgot my question. When we are trying to estimate the true mean, what do we use to estimate it? For 100,000 points. We'll have more screens to come. When we are trying to estimate the true mean, what do we use to estimate the true mean? When we're trying to estimate the true mean, the sample mean, Walker right there, we use the sample mean. Listen to it again. Now I'm going to change it. When we estimate the true proportion, what do we use to estimate the true proportion? What is our best estimate of the true proportion? 100,000 points again, first person, who's got it? What is our best estimate of the true proportion? What is your best? Boom, Sydney right there, got it. So great job. 10,000 points if you're after, but still answer. Even if you're second, I'm throwing 10,000 points for all those people after. But the sample proportion is the best estimate of the true proportion. The sample mean is the best estimate of the true mean. That's why we are using these things right here to create intervals for either. This one creates an interval for P, and this one creates an interval for mu. It creates an interval for the true mean. Okay, so let's jump right into this. We've got an understanding of what we're talking about today. We've got a big concept here, which I covered some yesterday, which is the central limit theorem. The central limit theorem is going to be a big condition for this. The condition is going to let us use the normal distribution. The central limit theorem is so key to statistics because it allows us to say things are approximately normal. This is the biggest thing why we use it, because we can have distributions that are not normal that all of a sudden become normal due to the central limit theorem. So we get into some fun stuff right here with the central limit theorem, and let's talk about it. We have condition 1. Every time I say condition 1 for test 2 and 3, you should know random. I want to see it in chat. Let's see it in chat for 10,000. Condition 1. Random. That means we randomly select individuals. I can't go to like a UT basketball game and talk to basketball players and ask them their height. That would not be random. So we don't get a good representative sample. This goes to sampling chapters. If we don't take a random sample, 10,000 points, all his answers in the chat. Quick question, you said something about the means being used for quantitative data. Does that mean the proportions will be used for Rachel, 100,000 points. Qualitative, categorical is proportions. Great answer, Rachel. You are correct. Like, do you like Taco Bell is categorical, proportions. How tall are you is quantitative, so means. Rachel, amazing answer. So, and tag, if you want, tag me in those and I'll see them a lot better. I saw it was a big thing, so I made sure to read it. The second condition here is 10%. What does 10% mean? It means, and it's a weird one because it kind of like, your hand's like, why is it 10%? 10% means we need to sample less than 10% of the population. We need to sample less than 10% of the population, which is so like counterintuitive. I could go into like a 30-minute lecture on why it's less than 10%. Right there, Tracy, 10,000 points. No more than 10%. Exactly. We do not want to sample more than 10%. Sample less than 10% is the easiest way to remember it. And it's like a really complicated thing, so I'm not going to bore everyone because everyone will start leaving the video and being like, this is no fun anymore if I start going into why. But for now, just memorize it. We're not doing super advanced statistics, so we'll just understand it is a condition that exists. But the one we should go a little bit in depth on is the large enough sample condition. And I usually call this large enough n because n stands for sample size. And we did some notes on it yesterday. So let's pull it up right here. Do I still have that one up? Yes, I do. This was the sampling distribution question from this chapter about, oh, pause, 10,000, 100,000 points. Jake right there. Pause, please pause. We get into this right here though. Jake, amazing answer. We want to make sure we choose the right third condition. The third condition, if it's categorical, as Rachel was pointing out earlier, will be success failure. So have your pen out, write this down. If we have categorical data, the third condition will be success failure. So when you're dealing with proportions, it's success failure. But when you're dealing with quantitative data, it will be the large enough n condition, n is sample size. So large enough n condition right here. Now, something really cool happens, and I think I still have it up. And I'll need to bring it up. Okay, let me pull it up. Okay, here we are, and let me bring it down to the screen here. Okay, So let's take a look. Let's hit begin. Here we are. This is the central limit theorem, and Tracy already knows the numbers. Because what we're going to notice right here is two things. We're going to notice thing number one is that when we increase the sample size right here, this distribution down lower will get tighter. So let's increase it. You can't see it off the screen right there. Let's increase this to 10. And now look, it gets tighter. And then let's go here and increase it to 25. And look, it gets tighter again. Why does that happen? We're going to explain why here in a moment. But then also, thing number two is the following, and I'll repeat these. That the distribution up here can be skewed, and then the distribution down here can look what? Wait a minute. That second distribution actually looks kind of what? It looks basically what? Who knows for 100,000 points in the chat? 10,000 points if you're saying Sarah is right. Sarah's right. It looks normal. Sarah got the big points. Everyone else type in normal. You get 10,000. Remember, follow along, type these answers. You're still getting 10,000 points. Big answers to the first person, big points to the first person. But you should realize, wait a minute, it looks normal. But we have a problem here. What if we only use 2? Does that look normal, yes or no? Does that look normal, yes or no? Does that look normal, yes or no? Does that look really normal, like as normal as the last one looked? No, it doesn't. Carson, 100,000 points. Everyone else, 10,000 after Carson. I didn't say 100,000, but it was a secret one. So, Carson, you are right. That does not look normal right there. But wait a minute. As we increase n right here, the distribution becomes two things. 100,000 points. What two things happen as n gets larger? The distribution becomes two things. You got to type the two things in the chat for the central limit theorem. These are the two key concepts of the central limit theorem. That is, n gets larger, the distribution tighter and more normal. Carson, you're on a roll right there. And Sean and Stephen and Emily and Walker and TW and Sydney and Avery, all of you get the points. And Alexander, why not? Everyone answering gets 100,000 points. Up to, keep answering. Keep answering. Who's got it? Up to Luke. There we go. And Wilson, why not? There we go. So yes, everyone got the 100,000 there who was answering. Keep track of your points. Keep answering questions. That's how we learn. The central limit theorem states that as n gets larger, the distribution of the mean, did everyone hear that key word, will get more normal and tighter. The central limit theorem states that as n gets larger, the distribution of the mean will get more normal and tighter. Once again, I'll repeat it 3 times means it's very important. The central limit theorem states that as n gets larger, the distribution of the mean will get more normal and tighter. This is the original distribution. Like, let's say it's the heights of UT students. What we're doing right here, let's show it, is we're going out and we're talking to how many UT students? Someone in the chat tell me, how many UT students are we talking to? How many UT students did I just take as a sample? Does anyone have any idea how many UT students I just took as a sample? 25. And then this observation right here is the average of those 25. So watch again as I talk to 25 UT students, and then I average up all their answers, and that's their answer. So this distribution down here, every blue dot is the what? Every single blue dot down here is the what right here. There's a blue dot again. The mean, yes, Sydney, 100,000 points. It's the mean of these 25 observations. So this is the distribution of a mean of 25 observations. So every single blue dot, they average each of the sample of 25. Sarah, 100,000 points, Sarah. Perfect long answer right there. This is, I think, the hard concept for people to get sometimes is we're not talking about one observation. Like literally, if you watch one block go down, that's one person's height, another person's height, another one's. We're just talking to people and saying, what height are you? What height are you? What height are you? And they're taken randomly, hence the randomization condition. And then after we get 25 observations, don't know the gap there, we average them together and we make a distribution of the averages. And we can do this repeatedly. And when you do it repeatedly a whole bunch, you'll see it looks a lot more normal. So what's going on right here? Well, the truth is this. Think of this, that the more skewed it is, we'll do a custom one right here. Whoops. Go custom and then clear it. Oops. There we go. So if we make one that's ridiculously skewed, I want it to, yes, perfect. Okay, good. Oh no, I did it wrong. It's so close. I'm trying to do something here that I want to do for it. We'll see. Oh, so close. That was it. I had it. People might know what I'm going towards. Okay, that's close enough. That's close enough. Okay. So this is, so why would things not be more accurate? Sample size is too high. Tracy, I don't quite understand. Yeah, Jack knows what I'm going for. Exactly. Yep, you saw it. I was cheating for it. The more common there are outliers. I don't quite understand. Rephrase the questions and I'll try to answer again. But I did something really important here. What you're doing right here is you're literally, let's say we ask people how many push-ups they can do. It'd probably be a right skewed distribution. Like we'd have a center around like 1, 2, 3 or something, and then it would you'd have that peak and then it would follow over. So we have a right skew distribution. And so with this right here, so the reason, Tracy, that's such a good question. I'll speak real briefly on it. It has to do with the way these statistics are calculated for the less than 10% sample. Not every thing in statistics uses that, but these are very classic statistics, and it's totally counterintuitive. And I've read some really good articles on it, and basically there's more error when you sample more of the population. But you are correct, things would be more accurate, but it deals with finite populations. So the reason it runs into a problem is the way the statistics are calculated using finite populations create an error in the calculations when you sample more than 10%. Some people are more stringent on it and sample less than 5%. And so great answers right there. Sarah, 10,000 points also for helping out, and 10,000 Tracy for asking. And so right here, here's the big concept for this. You ready? I want people to tell me, when we talk about the distribution down here, as n gets larger, you'll have to see it down here, as n gets larger, like we sample larger sample sizes from this, the distribution of the mean will get more normal and tighter. So tell me, does my distribution up here look skewed or very skewed? Does my distribution look skewed or very skewed? Does my distribution look skewed or very skewed? 10,000 points in the chat. Does my distribution look skewed or very skewed? Very skewed. You are right. Very, very skewed. The more skewed a distribution is, the greater chance. The more skewed it is, Tian, the more skewed it is, the larger sample we need. So think about where 25 worked before. Who thinks 25 will make this look normal? The new distribution of the mean will look normal, or the new distribution of the mean will not look normal? Remember, this is very skewed. So who thinks it'll look normal at 25 or not normal? Well, let's start with something really small. I like the knots in the chat. If we start with 2, and we literally take 2 observations and make a distribution that averages 2, do you see how that was between those right there? All we're doing is taking 2 points and averaging them. So you see how it's literally just the average of 2 points. Look at where the black dots are, and then boom, right between them is the point. And then we do this repeatedly. This does not look normal. And then if we go up to something like 10 and average together 10 points and get blue dots from it, well, oh wow, it's actually looking kind of normal. Central limit theorem is an amazing thing. I think I have to do it the other way. I've gotten it to not look normal before. It's still got a little bit of a skew. Let me do the one I usually do. Oh, I lost my standard deviation now. They knew what I was going to do. They knew the trick. I think when I do this, now it won't look normal because that's ridiculous. Yeah, it's still got a skew on it. And so what you'll notice here is the larger the sample size, the more normal it becomes. See, that's not normal at all. But as we go up in sample size, it becomes more and more normal. So here's the key notes you should know from it. You should know, and let's go over to the notes I have from yesterday, that when it is normal, how large does n need to be? When it is normal, how large does n need to be? 1. Let's test that out right here. Let's see if that actually works. Because if it works, we should have something that looks normal, and then it doesn't let us put in 1 here, and then we should just be able to go like this. And does that look normal? Does that look normal right here? Does the lower graphic actually look normal? It does. Because remember, it's just going to make that look more normal. So if you have something that's normal and it becomes more normal, it's still normal. It's like saying you have an A already and I increase your grade. Well, then you still have an A. So since it was already normal, then we don't need a large sample size. So that's the first one right there. But then if it's skewed, and what does skewed mean? That's so subjective. I do realize it's subjective to say it's skewed. But when it's skewed, then we see that we need a sample size of at least 25. So with a sample size of 25, we can handle skew. But if it's very skewed, we need a sample size of what? For very skewed data, we need a sample size of at least 100. So what do these graphics represent? Normal, skewed, and very skewed. So what do you notice? The more skewed it is, the wider n needs to be. The more skewed it is, the wider n needs to be. Who can say in the chat for 100,000 points? The more skewed it is, the wider n needs to be. Larger, bigger. We got everyone up to Sean right there. Yes. Why not up to... Let's see. You guys are awesome in the chat. Miles, there we go. The more skewed, the larger n needs to be. Exactly. So if it's not skewed at all, if it's perfectly normal, the larger n needs to be, because that'll normalize it. And you know what's interesting? We see right here the other concept. And we'll start looking at this in the notes here. I'm going to go back to the notes right here. But this is the other concept, that the distribution of the mean will also be tighter. So let's hop back in here to the notes. Great job, Raneem. I'm making you a mod right here, and you get 100,000, Raneem. Amazing answers in the chat right there. So great work. So let's hop back into the notes. And here are our notes over here. So that is the large N of n condition right there. And once again, if it's normal, 1, 25 skewed, and 100 very skewed. Keynotes you should know. Let's continue on. Here's what the distribution looks like. You're just seeing the notes in action. If you notice, that one is very, very skewed. So you need like a very large sample size right here. Since it's extremely skewed, you'd probably need close to 100. Sometimes you need 200, but probably at 100 it's good. But here's the secret fact we don't tell you, is that it can take really large sample sizes sometimes. This is a big thing, though, that distributions will become more normal due to the central limit theorem. And so the more skewed it is, if this one up here is ridiculously skewed, it might take more than 100. Because what if it's more skewed than very skewed? What if it's ridiculously extremely skewed? But don't worry. Once again, keep the numbers in your head. 1, 25, and 100. I know 1's not on this slide, but if it's normal, you don't need it doesn't matter. It's already normal. So the central limit theorem helps us say that the distribution will be normal and tighter. More on that in a moment. So what do we have going on right here? From previous talks, we should know that the mean for the distribution of the sample proportion is the true proportion. What does this mean in words? It is to say, if you go out and spoke to, let's say, UT students, and you know 70% of them like Taco Bell, I use the same consistent example, what would you expect to see in a sample? So if it is the truth that 70% of students like Taco Bell, what would you expect to see in a sample? What would you expect to see in a sample? Hint, they're equal to each other. Exactly, Sarah, 10,000 points. If 70% of students like Taco Bell, you would expect to see in a sample 70% of students like Taco Bell. But if the average student is 5'9", what would you expect to see if you took a sample mean? So this is the true mean. What I've highlighted right there is the true mean. And if the true mean is 5'9", and you take a sample, you'd expect to see in your sample 5'9". That's not saying you will see it. It's just saying the center of the curve would be 5'9". It's like, well, if, once again, I've highlighted right there, if the true height of students is 5'9", then can you explain all the meanings of each letter? Yeah. So, and I'll go through them each right here. We'll do that next. Great question, Raleigh. 10,000 points. Thank you for the question. Keep asking those questions when you have them. I see the chat at all times. So I'm lucky. I was born on the internet. I was born on the internet. It's a horrible Bane impression. But all right. So we have here right here the mean, and so this is the population mean. What I've highlighted right here is something like the true height, very much so. The true height of all UT students. What we've highlighted right here is the population mean, which is the true height of all UT students. What I've highlighted right here is what we expect to see in a sample. And I know it says true mean right here. That is the true mean or the population mean, but it's much easier to think of it as when I take a sample, I expect to see this. It's the expected sample mean. So it's kind of the truth for the long run of taking samples, which that gets into more theoretical stuff for statistics. So you could say it's the population mean of the sample mean. Sounds confusing. If that confuses you, understand it better as when I take a sample, I expect to see this, because the mean is what you expect to see, and you expect this right here. This is the expected mean for the sample mean. Same goes for up top. P is the true proportion. This is, if an example right here is the percent of students at UT who like Taco Bell, not from a sample, but it's like if you knew 70% of students like Taco Bell, that would be P. It is the truth for all students. Then when you go over here, it's what you expect to see when you take a sample. So that's to say, you know, if I take a sample, what would I expect to see as my sample mean, or sample proportion, excuse me, that is sample proportion, and I would expect to see the true proportion. So all this good stuff right here. So good stuff. Okay, we're on to some new stuff right here. Classic stuff right here, P times Q over N square root. So when you think about this right here, P is the true proportion, truth for all students, you bet. Nice job, Tracy, 10,000 points right there. So P, Q, N square root, and then we have sigma over square root of N. Sigma over square root of N is just the true standard deviation over the sample size, and this is the variation in the sample mean. So when you take a sample, what kind of variation would you expect? Same thing when you get a sample proportion, what kind of variation would you expect in the sample proportion? Variation is simply, we'll go back to the slide where I drew it all out yesterday. Variation is simply just these standard deviations right here. So those right there are the standard deviations. And this is for y bar. And this one right here, this 9.5 in my problem, what is that 9.5? Can anyone tell me in the chat what the 9.5 is? The larger the n is, the smaller. Yes. Yep. Tion, 10,000 points right there. You are correct. If n is larger, it'll make it tighter. Exactly. And that is mu. Great answers in the chat. That is mu y bar right there. So that is mu y bar, and it's also mu because mu y bar equals mu. So you can see up here where I was solving for that yesterday, and this whole problem is worked out online, and we also reviewed this chapter. But that is mu y bar equals mu, and so that is the, and be careful, that wouldn't be the sample mean, that is the expected value of the sample mean. So that is the true mean, and it's also the expected value of the sample mean. So that is the true mean, because this is the waiter waitress problem. The waiter gets on average 9.5 for their tips, and then we see right here that we expect in a sample, we would see about 9.5 on average. So samples come from here. The samples are the dots. The samples are tips they could get, and then the red distribution represents the average of multiple samples together. So the red distribution is like the mean of 40 tips. So the red distribution, if you look at it, the original distribution is already normal, but the red distribution would be more normal, so it's still normal, and it'd be tighter. So if you notice, it is now tighter by a factor, and let's show only the highlighted thing I want to show. The red distribution is now tighter by a factor of what? What did we do to the original standard deviation? The red distribution is now tighter by a factor of dividing it by what? What did we do to the original standard deviation to make it tighter? We took the standard deviation of 5.4, and we did what to it? We took the standard deviation of 5.4 and did what to it? Square root of 40, exactly. So 100,000 points, Sarah, right there. Great work. We took the original standard deviation and divided it by the square root of 40, making it tighter. So does everyone see how that red distribution is tighter? This is because it's the distribution of the mean. Remember, we were just talking about this. We were just talking about how this works, that when you increase the sample size down here, it's going to do this. And for those with a keen eye, here we'll remove this, I want people to tell me, when we make the new distribution down below, what will the new standard deviation of it be? 200,000 points. 20,000 points for people who come in second with the answers. What will the new standard deviation be for the distribution? Ah, Sydney, you got it. You are right. People are wondering, how do you know that? If you remember the formula we're doing right here, it's going to be the original standard deviation. You're still getting the points, 20,000 points for everyone saying it right there. But I want everyone to look at this. 5 divided by what? 5 divided by the square root of 25. 5 divided by the square root of 25 is 1. Now wait, why is the mean for this one still the mean for this one? Does everyone notice that the mean up here is still the mean down here? Well, that's the formula we just saw a moment ago. that the mean for the distribution of the sample mean is equal to the mean. So the mean does not change. The mean for that red and black distribution stay exactly the same. But what changes about these distributions? The mean stays the same, but what changes about these distributions? The mean stays the exact same, but what changes? The mean stays the same, but what changes? I want to see in the chat for 10,000 points. The mean stays the same, but what changes about these distributions? The mean stays exactly the same, but what changes? Any ideas? Standard deviation gets smaller, exactly right, because it gets tighter. So this is what we're seeing visually right here, is that the standard deviation gets tighter by a factor of the square root of n. Great job, everyone's following along. So that is what we are seeing right here in action right now. There we go, we've got the stuff right here, and we've got the balcony problem. I might go back and work that a little later. And now we get on to the new stuff today. Okay, we got 20 minutes and we got time to do this. You ready? So we'll do more example problems. Remember, I'm gonna do lots of office hours and I've worked some example problems. So please, please, please check out the video. I think some people were watching the video yesterday where I did the waiter-waitress problem. Has anyone seen the video where I did the waiter-waitress problem and you were able to solve it? I think I know a few people in chat were there. But has anyone seen the waiter-waitress problem from the video and they were able to solve it using what we did in the video? Because we pretty much just covered all that. Yes, that's awesome. And that's what I want. We'll be doing more videos, and I'll be going through more problems, and then I'm going to try to, lecture time, focus on lecture. Awesome. So keep using those videos and keep asking for more problems. Someone asked if I could go over the formula sheet, so I came on last night and did that. If you see me live on YouTube, do that. And if you guys want, go ahead and hit that subscribe button. We just monetize. You don't have to. You don't have to subscribe. Hit like on the videos. I'll make a quick announcement right here. I just went to monetize the channel. So the channel is under review for monetization, and any money we get will be pretty much put back to you guys. That's my plan with subscribing. Thank you so much. Always hit like on the videos, because as soon as monetization goes through, I think they'll start looking at how many likes we get versus dislikes. Apparently both are good, but I don't like dislikes. But thank you so much. And then if we do get money, which we should start getting some money, we're just going to put the money back to you guys. So my dream is, and we might start broadcasting on Twitch, but if we start getting in, like, let's say something awesome, like $2,000 a month, I'd love it if we could make a scholarship. Like if we could give out scholarship to people, you know, like in Haslam College of Business or whatever, but we could do like, yeah. So I want to put out really great content, and we just got the okay to monetize. So every time you subscribe or you like it or you share a video, you're really helping us out. But, yeah, I don't know. We're in the YouTube game now. We're in the YouTube fighting for the views. But thank you guys so much. And I'm only going to try to put ads on video. Like, I'm not going to put on these live lectures. So when we get ads, you're not going to come to a lecture and there's going to be ads. But and yeah, once again, all the money will go back to students. That's our plan with it. So I really appreciate it. So that's the plan. Like and subscribe. You know, classic YouTube stuff right there. Make sure to hit that bell for notifications. All the YouTube sayings. Okay, let's talk about confidence rolls right here now. So 95% confidence rolls. Oh man, you would think. You know everyone who's memorized that 1.96? So everyone has memorized 1.96, and you would think that you could just use that all the time. And I'm pulling up a thing right now to show and help out with. I'm trying to think of... You'll see what I'm showing here in a second. I'm trying to find the perfect picture of him, because this gets to one of my favorite parts of the lecture. I like this picture. There we go. Okay. So you would think it would be 1.96. Well, Khan Academy, they got a really good YouTube game. They're a great channel. So here we are. You would think you could use 1.96, but Mr. T says no. It's such a small picture of him. Usually I pull it up bigger in class. Mr. T doesn't like that. What Mr. T did is he traveled back in time, and he found the normal distribution. And he took that normal distribution. My horrible Mr. T impression is going to be put on YouTube today. It's already been on there. And he said, "I'll pay the fool." And he smashed it down. So Mr. T took the normal. We get space pen right here. And Mr. T's there. And he smashed down that normal. and he made the t distribution. I have had seniors tell me that they remember the t versus the z this way. Kind of looks like a foot coming in there. But does everyone see? I've talked about the t in the past, and we even started today's lecture talking about the t. We drew out our previous confidence interval of p hat plus or minus z star, and then p hat q hat over n square root. And then we said, wait a minute, today we're going to be talking about y bar plus or minus t star n minus 1 degrees of freedom, and then s over square root of n. And this will all be written out a little nicer for you to see in a moment. But Mr. T came in and he smashed down the normal distribution. Now I know, like, it sounds so crazy, but the true story behind this is about as crazy. The guy who actually did this, it wasn't Mr. T, I feel so bad. The guy who actually did this worked at, we'll pull up his picture right here. It's so funny. There's one picture of him, and he's actually younger than me now. There's Mr. T again. We're going to pull up. The guy who actually did this was William Gossett. So William Gossett right here is the actual creator of the T distribution. So William Gossett actually created it. He worked at Guinness Beer. So Guinness Beer is to thank not only for great beer, but Guinness Beer also helped create the T distribution. And what's even crazier, and I've learned so many more things about this, that William Gossett was actually in like a feud with another famous statistician, and he used the pseudonym means fake name, Student T, to get it published because they wouldn't publish his work. Because like he was trying to submit it and being like, hey, here's some really good things we should all do and know about, the distribution. I've made this new distribution, and it's like the normal, but it accounts for degrees of freedom based on sample size. And they're like, nope, not putting it out there. And then he published it under a pseudonym, Student T, and they put it in the highest journals, and now it's a huge thing. So everyone uses it. But I want everyone to understand that when we talk about the T distribution, let's do this right here. The T is just like the what? I want to hear it in chat. The T is just like the what curve. The T is just like the what curve. I need to hear it in the chat. 10,000 points. Quality control for beer. He must have been taking lots of samples right there. Boom, Sarah, 10,000 points. You were right. The quality control for the beer and the yes. So the T is just like the normal, the Z. You are right. Everyone's saying normal and Z. The normal curve is the Z curve. That's where we get Z scores from. You are correct. Watch this. Can anyone tell me, if I were to go here and go above 1.96, what area should be above 1.96 right here? On the normal curve, what area should be above 1.96? Be careful. Remember, it's a 95% confidence interval. So remember, 95% in the middle, with 95% in the middle, 100,000 points. With 95% in the middle, what area should be on the outside of the curve above 1.96? Remember, it's 95 in the middle. You got it, Raneem. Amazing answer. You earned that 200,000 points. Oh, it went away, but it was there. You are exactly correct. But wait, and you guys remember, we've already done some of these problems with chapters. 645, that's 10%, or is it 449 if you do the extra decimals? There it is. And then 2812, there's that. And apparently, it's 6. I've learned that over. And then there's more decimals I don't even know. And then you guys have heard me say things like this in class, like 2.5758. And there's that. And last but not least, we've got another one. I think I just hit insert, but 2.3263. All of these work, and I'm getting numbers like 1% because I know the Z scores for confidence intervals. But wait a minute, why are we learning this if it's just the normal curve? What is this right here? What did Brian call that for 100,000 points? You should know what that is instantaneously. Every T has with it this. You need this keynote. Write it down. Every T has these. Degrees of freedom. Sarah, you got that 100,000 points. Amazing answer. 10,000 for everyone else typing it. Keep typing those answers. But every T has degrees of freedom. You must know that because you can't just say a T statistic. You have to tell me what are the degrees of freedom. So what are the degrees of freedom? Well, Mr. T is such a nice guy that Mr. T will give that curve freedom to be normal. So Mr. T, when he gives it freedom to be normal, lifts his fist off of it. And then what happens to the curve when he lifts his fist off of it? The curve becomes more normal. So he lets the curve go back up and be normal. Now, how many degrees of freedom would he need to make it perfectly normal? Infinite degrees of freedom. Mr. T would need infinite degrees of freedom to make the curve more normal. So it's never truly normal, but it's kind of normal after certain points. Do you want to see Mr. T smash down the curve? Let's make it happen. Let's make Mr. T smash down that normal curve right here. Let's go over here and let's type in 1 degree of freedom. That means Mr. T is only going to give this 1 degree of freedom to be normal. Smashed. If you looked, it's further out. I know the one I like better. Let me pull up the new page because this one doesn't show it the way I like it. We're going to go to stat distributions. And let me pull it up on this page because this one makes it look more like he's smashing it. The other one changes the aspect ratio. All right, so let's pull it up here and let's look at this one because this one shows it the way I like it. Okay, so here we're going to give him 1 degree of freedom. Smashed. 2 degrees of freedom. What is happening to the curve as I give it more and more degrees of freedom? Can anyone tell me the curve is becoming more like the what curve? As I give the curve more degrees of freedom, so you notice the degrees of freedom are going up right here. Look at it rising up. It's becoming more normal. And look, as I go up and up and up, all of a sudden now, if I put 95% in the middle of the curve, let's go here. Oops, I'm on the, no, it's not. There we go. If I put 95 in the middle of the curve, then all of a sudden the t-score is 1.96. But it won't always be that way. You won't always get 1.96 because you don't always have this amount of degrees of freedom. If you had 1 degree of freedom, well, now you can't even see it. Let's go to 4. There's the t-score, and if you notice, it starts to go in towards it. And these are all 95% confidence rolls. This is where people get stuck when they're doing their homework assignments because the z-score for a 95% confidence roll is always 1.96. The t-score for a 95% confidence roll, you must know the what. A t-score for a 95% confidence roll, you must know the, for 100,000 points in chat, tell me. To find the t-score for a 95% confidence roll, you must know the degrees of freedom, right? Sarah and Sydney, great answers in the chat, and everyone else be answering in. Remember, you can still get that 10,000 even if you're second or third. So, and for all the people, the degrees of freedom. So how in the world do we find degrees of freedom? Well, the degrees of freedom, there's Gossett with his T, there's it right there. The degrees of freedom are a very complicated formula. Does everyone want to see the complicated formula for the degrees of freedom? There it is. Super complicated formula. N minus 1. That's all it is. For one sample. Now be careful. This is one sample, so put it in your head. One sample is N minus 1. So the one sample degrees of freedom is N minus 1. So if I were to take a sample of 50, what would the degrees of freedom be? If I were to take a sample of 50, what would the degrees of freedom be? Like, what would I go in and put into the calculator? I'm like, I need to calculate a 95% confidence roll. My sample size was 50. Let's see, did anyone get it in the chat? 95% confidence roll with a sample of 50. 49, you're right. And there's the t statistic I would use. So if you notice, there is the t statistic I would use. And look, it's basically 2. Because remember, 68, 95, it's basically 2. And of course, if this goes higher, I think it's 60, it literally says 2. So I've always liked 60 as the degrees of freedom, because then it's like so close to 2 that you can just use 2 and you're actually using the right number instead of 1.96. But the t changes. What if I showed you this problem? Like, what if we had output on the final test and it said, what sample size was used to make this confidence roll? What sample size was used to make this confidence roll? Anyone have an idea? Remember, it's N minus 1 for degrees of freedom. So what sample size was used to make this confidence roll? 72, Walker, 10,000 points. Why not 100,000? We've been getting big points today. Remember to keep track of all these points and to put them in the sheet. I'll be adding those up in a little bit here. What's the difference between a Z and a T? Great question. So the z-score is used when we know the true standard deviation. I've got the wrong things over right here. It's a very good question. So you would use a z-score if you know this right here. It's better statistics to assume you never know that. So instead of using the true standard deviation, we now use the sample standard deviation. Does everyone see the small change from here to here? The problem is that when we use the sample standard deviation, we can't use the z-score. So when we go from the truth, we use a z-score, to when we go with the sample, we use a t-score. So there's actually an interval we don't teach in this class, which uses a z-score, which assumes you know the truth, which would be this. but we don't know that usually, and it's better to assume t intervals are wider. So usually people use them in statistics more often because they're a more kind of liberal interval. They cover more values, and so we use this one right here because we usually say, well, do we really know the true standard deviation? I don't know if we really do. So we use this one right here. So the z-scores are used when you know the truth, and t-scores are used when you only have the sample. So we have that right there. And then let's go right here. Condition 1. Who knows condition 1 for making a confidence roll? Any ideas on condition 1? You know it right now. You're super quick on it. Who knows condition 1? 10,000 points in the chat. It's random. Of course it's random. You got it. Condition 1 is random, which means we take a random sample of individuals. Condition 2 is 10%, meaning we sample less than 10% of the population. And condition 3, it says nearly normal, but here's the thing. Here's the thing. We can still call it large enough n, because guess what? Large enough n is still a portion of this. And I hate how the numbers have changed in this. This is what they do on my Pearson. They're like, well, now it's 15 and 40. It's still the same idea. Is if the distribution is normal, we don't need a large n. So the biggest thing right here is that we could have something that is skewed, and your problem could say the distribution is skewed and we take a sample size of 200. Do we pass, and you can call it large enough n, that's perfectly fine, but do we pass the nearly normal condition here? The sample is skewed, and we have a sample size of 200. And what would you write? The sample is skewed, and we have a sample size of 200. Do we pass the condition? Do we? We do. Because, and the key thing here is, we're not looking to see if this is normal. We care about the distribution of the mean. So if the original distribution is normal, which this is kind of getting to right here, if the original distribution is normal, we're good. But if it's not, the larger, this is large enough n again right here, that since we're taking a sample size of 200, then the new distribution of the mean will be more normal and tighter. So the red one I drew right there, it's probably even tighter than that. It would look something like this right here. The new distribution of the mean will be normal and tighter, and that literally goes back to the huge concept we saw of the central limit theorem. So you could have a skewed distribution like this, take a sample of 200. I know this won't be 200, but we'll pretend. And remember, it's like you took 200 observations and made a distribution of the sample mean, and the new distribution will be normal and tighter. Exactly. Exactly. Sydney, amazing answer, 10,000 points, Sydney. Keep up the great work. That's exactly what we're getting at right here with this third condition. It's called nearly normal, but you can call it large enough n. That is perfectly fine. And we've now covered all the material. I'm going to hope for, I don't know if we have time because we did a lot of coverage at the first part because I usually have enough time to do an example or two. Here, let's end class with this example. You ready? Okay, we're going to do an example of the confidence roll. Here we go. We might go a tiny bit over, so if you have to leave, that's all right. And I'll put up an end screen here, and I'll probably grab some more water or something between class. Okay, so let's talk about this example right here. Remember, whenever you have an example, pull out your pen, start writing on it. 90% will be used to tell us the what. 90% will be used to help us find the what. The y bar, the t, the degrees of freedom, the s, the n. What will 90% help us find? 90% is going to help us find the what. That is information we need. In this problem, the t-score, Walker, you're right, that's going to help us find t. So that's going to help us find t right there. That is not t, but that's going to help us find it, because now we know it's a t for 90%. 23 is equal to what? 23 is equal to what? I need to see answers in the chat. Make sure you're following along. Write down these things as we go. 23 is what? We sampled 23 cars. 23 is what? 23 is n. 10,000 points for all those answers. Now that you know n, what can you immediately find from n? Now we can find the degrees of freedom. And degrees of freedom are going to be 22. So we know the degrees of freedom, and we know the n. We're almost there. We almost have everything we need to know. Did we randomly select these cars? Sure. Are they less than 10% of all cars? Sure. Is it nearly normal? When you look at this right here, I think we selected 23 cars, and I want you to tell me, does this distribution right here look pretty normal, skewed, or very skewed? Does that distribution down there look pretty normal, skewed, or very skewed? So in the formula you gave is t. No, t is the literal t-score. The degrees of freedom are the thing down here. The n-1 is the degrees of freedom. Don't multiply it by it. So, yep. And so this is pretty normal right here, so we should be good on this, and I'll have this problem finished in about 3 minutes. So thank you, everyone, for staying. Now all we need to do is put into the equation. I know it's a lot on the screen right here, but it simply walks through it, and it shows you how to solve everything, but here's where people get stuck. The biggest thing, because once you have the equation, it's not much more than putting the numbers in. Like just knowing that it says the sample mean of cars on that road that day was 31.04, the standard deviation was 4.24. This is where people get stuck. Is one, you have to know that this 90% is going to help you find the t, and you have to know the degrees of freedom are 22 because the sample size was 23. So we need to know that degrees of freedom right here, that's n minus 1. Now we go here, and we go to our applet, and we go right here to it, and we type in 22, and we want a 90% confidence interval. Does everyone, this is so key, this is where people get stuck on the assignments and say, how do I find the t-score? You have to know the degrees of freedom, and you have to know the percent confidence. This is where this t-score was found. This t-score was found right here. And from here, it's just as simple as taking, and was it 3 point, let me try to memorize these numbers real quick, and then we'll have it solved. From here, 3.31 and 4.25. I'm rounding them. Okay. We need a new sheet. I almost had it. I'll be ending in 2 minutes. So we go right here, and we have, I'm rounding these 31, and that's y bar, and then plus or minus t, n minus 1 degrees of freedom, star. We just take the t as it is, the 1.17. You don't multiply by the degrees of freedom or anything. Don't do that. And then you go here, and the standard deviation was 4.25 rounded over square root of 23. And this is right here, s over square root of n. Does everyone see? You can, so you don't have to use, nope, you can use, yeah, you can use calculators to do it, and I think I have some videos on that. Those will be things I'll monetize, but, because hopefully other people watch them. Where's the applet? Let me put it in the chat. It's my favorite applet to use for it. There's many applets for it. Stat distributions is really good, probably one of the easiest ones to look at right here. And I'll tell you what, I can put this link. What's up, Zach? Good to see you. So there we go right there. There's a link, and that brings you to the picture I have right here. If you get stuck on these, please ask. I've been replying to a lot of emails, so thank you everyone who's emailing me. But from here, we've literally made our interval, and we'll interpret it. But I think we'll end class with this right here. I don't want to go too much over. It's never my goal to go over time. Good to see you, Jay. Going well, just hanging out all by myself. So yeah, but so good to see everyone. But that's got it for doing confidence intervals. From here, we just interpret the interval. We'll do the interpretation, then we'll end, and I'll take some last questions. But if you look, we got through the notes. We're 90% confident the true mean speed of vehicles on Triphammer Road that day is contained in the interval 29.52 to 32.56. And that's got it for the examples. And then we just see output and showing how to use applets. But we'll do some review next class. Did everyone like the format? What did everyone think? Did everyone learn pretty well? You're not late to class. I'm just using one link for both classes, so that way I don't have to switch things. And we'll go through the material again. And no one's late. We'll probably see people joining in. What do you guys think? It was great. Thank you. Glad to hear that. Thank you, Alexandria, and thank you, everyone. Yeah, no, and I'm going to keep improving this. Liked it. If you guys know how to stream or anything, keep giving suggestions. Thank you, guys. Oh, you guys are so positive. Yeah, and I like doing it on YouTube here. It's just like, I don't know, YouTube's awesome. So it went great. Oh, you guys are so positive, and so I like it. And I'm going to figure out more about the polling and everything. So I'm going to figure out more that Streamlabs can do because I've just got time to like work on everything. Super, please give other faculty. You're welcome. Give me, maybe I'll email you guys and you guys can tell me what you like about this and what other people could do to improve because I'm going to be working with other faculty a lot. And I want to say thank you to all the faculty because I've been teaching online for 6 years maybe. Yep, tomorrow 2 p.m. Kahoot, and I'll send out announcements about that. So I've been teaching online for like 6 years, so I'm very used to this, that you have to make it an interactive thing. And thank you guys for interacting. Please interact. My online classes know that. I make sure from the start they interact. And so you guys did a great job. You guys did great today interacting. So the math department might need some help. Well, yeah, tell anyone to contact me. We're trying to help as much as we can. And I'm really lucky that I have all this stuff that I literally have for this. So what is the difference between the sample standard deviation and the true standard deviation? The sample standard deviation would be if we took a sample of 80 people and found the standard deviation. The true standard deviation would be if we knew for the whole population. So it's like from a sample of 80, we found a standard deviation of this. We know the true standard deviation for all people's heights is this. The first one was from a sample of 80, so that's a sample standard deviation. So that's the standard deviation of that sample of 80 students. Where when we say the true standard deviation, that is for all, like all students. It means everybody, which rarely do you know that. And then it's almost like, well, why are you making a confidence interval? If you go off known statistics. So a lot of times people might say we don't know the truth. Oh, cool. Rutherford, are they doing a great job? So it sounds like Rutherford's doing an awesome job too. And thank you. Like, I know a lot of faculty are working really hard. We've been training a lot of people and helping a lot of people. So thank you for everyone doing super hard work and for every student showing up too. So, so the standard deviation is different for, yes, it is. It is because you are 100% correct. Great job. You are 100% correct that the standard, why does the mouse move like that? You are 100% correct that the standard deviation here is different because in this one, you know the truth. This is like we work at a factory and we know the truth, which is weird to say, but then we really wouldn't use confidence rules anymore. Well, thank you very much. We were just finishing up the last class. So is Rutherford in the math department? We were just finishing up the last class, and I'm going to jump around for a second. Did you add some extra study information on Canvas? I don't think I did yet. We will be adding it. I'll be sending out a lot more today and tomorrow. I spent about a lot of time setting up the studio, so sorry if I was slow to get to some stuff. Email me any questions. I think I'm going to run around for just a moment. So we're gonna put up a screen right here. So here I'm going to do my favorite outro screen. So here we go. I'll be right back, everyone. Be back. Let me put it in chat. Be back in 9 minutes. Okay.
Hey Brian, what's up?
Hey, Adam.
Oh, what's this?
Adam, what are you doing? Adam!
No!
like TV from other dimensions has a somewhat looser feel to it.
Yeah, it's got an almost improvisational tone.
Hey everybody! So I might be getting the green screen back here in a little bit, but so good to see everybody. Awesome stuff. People should be joining class. I just started a few minutes early. So good to see Nafisa, Noah, Aaron, Jenna, Snay, and everybody. Nicolette, Reagan, to Kaylee, Dylan, Colby. Gosh, so good seeing you guys. Jake, I saw people saying, it's good to be back in class. Yes, good to see everyone. It's like, yes, and Zach and me. Oh man, it feels weird not being in the studio. Because, every other class felt like, they're not used to this. What's up, Roderick? So, and everybody, Neely and Yuting and Braden. Oh, man, it's so good seeing everybody. Make sure to be here live. That's how we learn. You guys are, Zach, other Zach. We got so many Zachs. It's so good. It's just like, I'm so used to Kid PvP. Hey, I'm so used to being in the studio with you guys. I feel like I'm in the wrong classroom. Meanwhile, I've been doing Zach Squared. Good to be back. Abby, you are correct. No, I do the other classes via this also, and people are liking this. So far, the response to this today has been really, really good on we like this format. This is pretty easy to follow along. This is really interactive. So I'm getting a lot of good responses from students saying they like this format. So I'm hoping, hey, I'm glad, we missed you too, Marina. So good seeing everybody. It's, I'm glad you guys like this format. I like it. I like being able to see everything. Chapter 14 will not be on the test, and office hours are online like this. So here I'll show you, we did some yesterday. So we only have 96. We need more people. Make sure everyone's here. If you're here, make sure to be here. So we do have more people. So I wasn't going to look at my people who were watching tonight, and then I saw. So I'm still happy, though. I'm still happy. We want as many people watching as we can. Let's go. And I've got huge news. A lot of fun stuff today. Logan, thank you so much. I'm glad you guys like this class. I'm glad you think it's a well-done online class. I'm kind of lucky because I've been teaching online for years now. And you see, here's the previous videos. So if you notice, I have the video here. Where, we're going to do a Kahoot at 2 p.m. tomorrow. It was voted on by the last class. I know how to do voting in the chat now. We can now do voting. I'll show you guys how it works in a moment. A slew of questions. We'll start with questions here in just a second. Teaching statistics, March 25th. We got, of course we got Abby, 100,000 points, Abby. You know why? Do you know why? Because it's random. Of course we got the random button. I'm going to try to make up new things while we're doing this right here. We're still going to have fun. I've got everything. I just don't have the green screen behind me. Literally, if I could put the green screen, I don't know. I just have to change stuff. It's the space I'm in right now is not really configured for the way I had the studio before. I had a standing desk, and I'd literally have to reconfigure everything in here. It's it's very interesting how I set everything up. So I can still do speed runs. Wait, let's see what happens with the speed run button. Oh, let's see. This is going to be scary. Let's find out what happens. I'm just over here. Let's see. Okay, I didn't set up speedrun yet. Let me fix this. I can still speedrun. Just need to... There we go. Yeah, so we can still speedrun. What's going on? Something's weird. There we go. Okay. So, and Jason, I told Jason I want to get him to be in some of the streams. We could Zoom Jason in. So we could probably Zoom Jason in. So more on that to come. But yeah, we could do speedruns still. We'll totally still do speedruns. And I might try to redo these screens. I could put myself in a box, make this look a little bit more professional. And we still got the transitions. I actually have other transitions we need to put in here. But let's go back over to the desktop right here. So we've still got all these things. Yeah, so there's I've still got everything going on right here. I've got all the good equipment and stuff, but I just don't have my green screen and stuff, and it's not really set up in the way. Anyways, we need Jason's Zoom cam. Yeah, we'll be telling him. He said he might be jumping in on stuff. You can still get the stickers, still totally getting those stickers. Yeah, we need a randomness transition, all that stuff. We still got the randomness button we did earlier. Here's one of the biggest things right here. Oh, we only had 60. Yeah, that's good because there were people watching it. But I got to delete that video. It didn't. We crashed midway, and I hope that never happens again. But I want to point out some key videos. Yesterday, I went online and I went through the whole formula sheet. So if you notice, this video yesterday for your test, which is coming up here, I go through and I talk about the whole entire formula sheet. So I've been trying to reposition my camera and get everything looking great right here. But you'll see me talk through the whole formula sheet and tell you what everything means in the formula sheet. So this is a huge video for you to watch and to understand what's going on with that. Then also yesterday, I was online reviewing problems, talking about how to do, and I don't know if you can hear the audio, which probably I hope not, but I was talking about how to do like the waiter waitress problem, the carbon monoxide problem. A lot of people have been emailing me saying, how do I do the carbon monoxide problem? How do I do the waiter waitress problem? So I went through and did each one of those on here. And there we go. And so that does that. Is the exam done through Respondus? Yep. So here we'll start taking questions now because this is a great time to bring up questions people have. I need to start closing my Word documents, but not yet. So let's answer all these questions. See lots of good questions on here. Also for the next exam, we get all of the bonuses if we get 100 on the quizzes. Does this include our one drop? Yes. The new exam includes the one drop. So you get your quiz score averaged into it with the one drop. So your drop is part of it. So it's a good thing. Today's class is going to be pretty much the same as the video you had us watch on Tuesday. It's going to be new material. We're going to cover the material on Tuesday. We're going to talk about the exam and the stuff, and then it's going to be new material today. Is the exam being done through Respondus? Yep, it'll be done through Respondus. Is the test going to be timed? Yes, it'll be 90 minutes. Is the test on March 30th? The test is Monday and Tuesday, which I think are the 30th and 31st. Someone correct me if I am wrong, but I think the test is let's just think through. Yesterday was Wednesday, and then 2 days backwards. It'll be 30th and 31st, if I'm correct. It's Monday and Tuesday next week. If we have 100 on the quizzes, do we need to retake them to get the weighted average? Nope. If you have 100 on the quizzes, you've got it. For the test and response, this is going to use the webcam. Yep, it'll use the webcam. Do you want the webcam for respondents? Yep, use the webcam. It's going to be open Monday and Tuesday. Yep. Is the test the same format? We'll be putting out a practice test. We'll have practice tests up this weekend for you to see what the format is like. We're definitely trying to make it as fair as humanly possible. And it's like, when I say that, it might scare people. Like, we're trying to make it as fair as humanly possible. And you're like, how can you do that? Well, that's the goal. It's to be as fair as possible with the test. And I think one of the biggest things we're doing, which is fair, is saying your quiz average will be averaged with it. I think that's a huge help because, for those who have done, the last 2 quizzes are open. So if you've been keeping up with your quizzes, getting good averages, then you should be all right. But if you haven't been doing the quizzes, you do get the chance to do the last 2 quizzes. And so you should try to get a computer with a webcam, or like try to get a webcam or borrow someone's computer near you, like a friend or a family member. And we'll try to figure out how this works for everyone. I know, because we're switching to online class, it's kind of like completely online. And then Sneh will point out, we will send out a kind of an example one where you can take an example respondus test this weekend. So expect that to come here in the next few days. Just the last 2 quizzes are open. Can we use scratch paper? Yep, you can use scratch paper. You don't need to do the quizzes again if you've already done them. My camera doesn't work on my laptop. I can use respondus, so I can't get the webcam portion. Contact us if there's no way that you can get a webcam. I don't have a webcam. We need a fair bind. I know, right? Oh no, Logan. And definitely, and that's the biggest thing we can do. That's why the quizzes, we really want the quizzes to help out. And I will say this, for anyone who's ever like learned a piece of music, I hate to say like you have to relearn stuff sometimes. I'm so sorry. But usually if you've gone over it once, it comes back to you quicker. So I'm so sorry. I think everyone knows it was just kind of the situations of the day. Are we allowed to have a notebook out or have scratch paper, have a sheet of scratch paper? How many quizzes are dropped? 1 for this section. Do we print out the formula sheet? You can print out the formula sheet. If you don't have a printer, you can write it down. You just need to show us the piece of paper. So if you can't print the formula sheet, if you don't have access to a printer, tell us and we will, you just write it down and we'll be good with that. Do you have to get a 100 on all the quizzes to count? Nope. Whatever quiz average you have will be average and we will be taking the higher on it. Will the camera on the Mac work? Yep. Will the practice test have a grade? It won't have a grade. Well, I think it might have a grade, but it won't count. It won't count. So it's just a practice to show what's going on. How do stickers work? Stickers work that if you get all 6 stickers, you get 2 total points on your average. That's amazing. So get those stickers. Stickers can be obtained by doing all the homeworks or all the quizzes and obtaining a certain average. For this section, you need at least a 95 average on the quizzes and you need a 100 homework average. So the homeworks are open right now. So if you're worried, start doing the homeworks, start doing the quizzes that are open. Hopefully you can get at least a 95 average, but you can still get the stickers for the 3rd section. So a huge thing is that, remember, I can curve. My system for a long time has been to curve up to 2 points on your final average. And if you don't like to participate, you can always get stickers. But remember, you do get points by participating. And I'm going to be very nice with the curve at the end of this semester. But you need to participate. Like if someone never watches the live lectures, doesn't do the homeworks and the quizzes, like I want you guys to take a guess in the chat. And I know I'm about to get for 10,000 points. If someone does none, like doesn't do the homeworks and the quizzes, doesn't participate in the chat, how much a curve do they get at the end of the semester? How much of the curve? No curve. Casey, you're right. No curve. And so how do you get that curve at the end of the semester? You get the curve at the end of the semester by participating right now, getting that 10,000 points. Let me scroll so I don't lose those last few questions. You participate right now like you're doing, and then also you can do the homeworks and the quizzes, because some people might be like, I don't like to talk. I don't want my name in the chat. That's all right. That's all right. You can still do the homeworks and the quizzes and get your points that way. This weekend, restudy time. Colby and Zach are relearning. And I'll be doing a Kahoot tomorrow at 2 p.m. Is homework and the quiz due tonight a part of the... And did I not move that? Did I not move it for you guys? Let me move your guys' homework and quiz due tonight. I thought I moved it. I must have just not hit save. But let me move the homework and quiz due tonight. As long as people want me to. If people say don't, then I won't. I'll keep it the same spot. But let me move the homework and quiz due tonight to be due on Wednesday of next week. So that way you guys can focus on the test. And there we go. So let me go here. Oh, I did move the one due tonight, and I'm moving it a little further. Sorry for all the... Wait, it's moving again. I'm going to put it to Wednesday of next week. Reason being is Wednesday of next week is after the test. So let's go here and save and assign. This... Okay, tell me if anything weird. It said there was individual settings. Tell me if anything weird happened with your settings. And I do want everyone to know this. I think people know that I am probably one of the easiest people to talk to regarding grades or anything. So we'll see this. Today's material won't be on the test. Will there be a way to see what we missed on the test? Yep. So on Tuesday, I think we're going to release what you missed. So you can see the questions and it'll show you what you missed. So great question right there, Rachel. What about having a calculator on your desk? I think we'll allow that. Just show us the calculator, open it up, show us there's nothing inside it. Average of the quiz group 2 will be averaged in. Let me think. I saw another. So if I didn't have a chance to get my sticker before the last test, and don't worry, stickers are just kind of, it's such a bummer. I literally, for those who saw, I literally have like 5,000 stickers to give to you guys. If you don't, I don't know how people do this class while watching the videos either. Point inflation time. But if you don't have a physical sticker, that's all right. It's that you have it. I can track who gets what, but it's so cool having the sticker in your notebook. How do we prove that we have the stickers? I look at the grades. Yeah, great question right there. Stickers are just a kind of thing for you. There we go. Can we still put in our points if we have... Yeah, put in your points as soon as possible. So that way I don't see like, I got 2 million points. And I'm like, what the heck? So put them in as soon as possible. Where do we go to find the test? It'll be online. I'll send out lots more information. So Madison will have some examples and stay tuned. So if you're at all stuck, we want you to email us as soon as possible. And I might even do some videos right here. What do you do if you have one sticker? Get lots of bonus points. Get lots of bonus points. And you can come get them as soon as my office is back open. You can come get those stickers. Project 2 grades are released. Zach, you are crazy. Zach, you are. And all the tests will be on Monday and Tuesday. Are there any more questions right now? Feel free to ask them. We've got a good 15 minutes of questions before class, and I really appreciate it. I appreciate all the questions. And remember, you can always email me, and I'll be on here. Okay, I'll change your grade to a 44.8, Zach. So remind me, email me and say, make sure my project 2 grade's a 44.8. I'll do that for you right there. So only if you want me to. And then you should have access to Jump. If you don't have access, please talk to us. Oh yeah, I did talk to one person about that already. I think we will be accepting Excel, and I'll be making videos on how to do things in Excel. So we'll find ways to do it. Excel has plugins that you can use. And I'll be doing lots of broadcasting. We also have some people who I might maybe have do stuff too. I've got some people I need to talk to the stat department probably this weekend, but one of our great TAs from Stat Lab, Connor, I might have him doing Stat Lab help. So, and Project 3 might be shorter also. So we're going to try to be as helpful and understanding with you guys as possible. So please tell us anything you think. Project 3 it's usually released it's usually due a week before, no, it's usually due right before the final. So expect it about the middle of next month. So 1 sticker for 100 on the, only this section, Joseph, is the 95. Last section, you had to get 100. Shoot for those 100s. There you go. What would we be doing with Jump on the exam? You won't be doing anything with Jump on the exam. You'll just use it for the assignments. I mean, for the assignments and the project. Great questions. You guys are so awesome in the chat. Actually, up 13 says, that's weird. Logan, email me. Pearson said, email me about it. Someone else had an issue like that, so maybe you started. Email me and I'll fix it. Test 3 is considered the final. That is correct. Great questions in the chat, and then we'll hop into doing lecture here. So I think any other last few questions? I think that's got it. Awesome. Well, thank you guys and gals very much because I really like all the interaction right here. Is the final cumulative? We do have things called here. I'll do one of the questions now. Great question, Nafisa. 10,000 points right there. Don't worry, that question gets asked a lot. The final is not really cumulative, but we have things called tools and techniques questions. So imagine I were to say, we want to understand the relationship between how long someone studies and the grade they make on the test. What graphical display would we make? How long you study and the grade you make on a test. Let's say pie chart, bar chart, scatter plot, or mosaic. So which one of these? Boom, right there. Both people right there. Everyone's saying it gets 10,000 points. You are right. The answer is a scatter plot. How did you know? It was a scatter plot when we look at how long somebody studies and the grade they make on a test? I mean, would you like that to be a test question? I think that'd be a pretty good test question. How do we know that? Who knows in the chat how in the world do we know that it's a scatter plot? We'll draw one out right here, and they might be saying in the chat already. But when we look at this, here's what a scatter plot looks like. Quantitative, Eddie is right for 10,000 right there. Be careful. It's both quantitative, 2 quantitative variables. So it's 2 quantitative variables is a scatter plot. So when you do that, what about if we said we want to look at people's pet preference and their gender? People's pet preference and their gender. What would be the answer? And QQ, that's right, because it's 2 quantitative variables for a scatter plot. QQ, straight enough, no outliers. So what would be pet preference? You were right, Jacob, for 10,000 points. Whoops, I'm not on the highlighter anymore. Jacob is right for 10,000 points. And all we're doing right here is checking to see if you know what graphic to use for each one. So if we were to do cat versus dog or something in gender, you could get a graphic that looked something like this right here, and we see a mosaic plot. So a mosaic plot is bivariate categorical. When I say bivariate, it's 2 categorical. Now, what if we say we just want to look at people's pet preference? Now it's a bit of a confusing question. Why would this question not be a well-worded question? Space Pen is back. Why would this, so 10,000 points right there, Jake, right there. Why would the question, we only want to look at pet preference, not be a good question? Like, if it's only one multiple choice. Pet preference alone could be used what? Oops, that's Space Pen. Space Pen's taken over. Pet preference would just be those. So pet preference, Barbara right there, 10,000 points. Great job, Barbara. Pet preference could be bar or pie chart. I know I can tell when you're off by like one letter. It's funny when I type in the chat and I'm like off by one. Caleb right there, 10,000. So bar or pie could be used for just pet preference because it's univariate categorical. Pet preference is univariate categorical. Do you see when I say like pet preference? Pet preference is just one variable and it's categorical. So these are the types of questions, Nafisa, that we would ask. We would ask questions that would see if you know the right things to learn from the class. So we're not going to ask you to like interpret the slope on a scatter plot. We're not going to ask you about the marginal or conditional distributions on a mosaic. We're not going to ask you to read a pie chart. We're going to ask you, when would you use a pie chart? But as multiple choice questions. That's what we've done consistently for the tools and techniques questions. There won't be short. There's numeric answer, but I don't think there's short answer. So it's very simple stuff. It's kind of like high level or like very like global idea of stuff. Like, do you understand when to use a scatter plot? So don't when you're reviewing for it, don't be like, what is the, four conditions, QQ straight enough, no outliers, plot doesn't thicken, how do they work? You need to know, when do you use a scatter plot? When do you use a bar chart? When would you test one mean? When would you test two means? We want to make sure you know how to use what you've learned in the class. Because if you know what to use, then you're on the right path. So the goal is to see that you know what to use, not that you know how to do everything in the class. So let's continue on. That is the tools and techniques. Guess what? Today, we're going to hop in here to new material. It is now time for new material. So let's see what I wrote to the last class. We get the benefit of me writing on the slides a little bit, but let's look in here. Oh no, I can rewrite it. What have we previously learned? And this is really front-loading us with knowledge right here. Here's key things we should know when we build confidence intervals for the mean. I want everyone to tell me that everything after the plus or minus is always the what in a confidence interval. Excuse me. Everything after the plus or minus is always the what in a confidence interval. Everything after the plus or minus. So the margin of error, yes, I thought you were saying me. I was like, me? So the margin of error. So the margin of error is everything after the plus or minus. You are right. Gosh, man, you guys know how to be in an online class. Other classes are doing great, but yes, all these responses, 10,000 points for all these responses. Anytime you're responding to a question I asked today, you get 10,000 points. Remember that. But we do have some big points right here, like things you should know. First person to tell me what p hat is in the chat gets, you know it's coming. I need to set up a button for this, but don't I already have a button? No, I don't have a button for it. You know it is. Oh, they're already saying it. Caleb's already gotten it. I'll take center of the interval too. It is the center of the interval. It is p hat. Of course, it's a random 100,000 points right there. Gosh, you guys are amazing. Just all these answers. Oh, that undoes that? Cool. I didn't know. I hit Control Z and it undid what I did in the studio. I didn't know it would do that. So we see here that this is the center of the interval. We see here, people are happy for the random still. Thanks, Jason, for making that, because wolves are cool. Jason knows what I'm talking about. So we see right here that this is p hat. And then we also see that we have a margin of error. And then we see that we have a z. Now, what does the z tell us? The z, having a star, means we can pick it. We can just choose one. Anyone we want. What is the z-score, though? It's the test statistic you pick. You are right. And it tells us the what. 10,000 points, all these answers. Not how many standard deviations today. I do miss Jason, too. The confidence level, Julio is right there. It says confidence level. You are right. The level of confidence, that's what Z tells us. 1.96 is a 95% confidence. 1.645 is a 90%. 1.2816, finally learned that, is an 80% confidence. So it tells us the confidence level. This right here is the standard error of the interval. So wait a minute. Let's review. The center of the interval, which is the sample proportion. The margin of error. The Z statistic, which gives us the confidence level that we get to pick. The standard error. The center of the interval, which is the sample mean. The margin of error. The T statistic, which tells us the confidence level, which we get to pick. The standard error. Does everyone see this right here? that if you were to look at these right here, these are both the center of the interval. If you were to look at everything after here, these are both the margin of errors. If you were to look at everything here, these both give you the confidence level. This has degrees of freedom with it, and you get to pick it. If you were to look at everything here, these are both the standard errors. You can choose it unless otherwise stated. Yep, so a lot of problems will state it. So everyone's getting study sessions together. We'll do as much studying as we can. So remember, this formula here is key, and we need to know how to use it. But we're going to start today with a little bit of review also, going over some new concepts. First of all, we have the central limit theorem. The central limit theorem is a new thing that we need to understand. And what does it mean? Well, we have a really good applet that shows it off. The central limit theorem says two things. 100,000 points. First person who can tell me what the central limit theorem says about this curve as n gets larger. As n gets larger, this curve will have two things happen to it. These are you need to write these down. Have your pen out. I always say have your pen out. So I'll take that. Elizabeth gets 100,000 right there. It'll get more normal. So the curve gets tighter and more normal. Abby, you are right. And also Abby, both Abby's right there. If you're doing it, 100,000 for everyone answering. Huge points today. Please keep participating because that's how we learn. It becomes tighter and more normal. So let's view this. Well, let's put n down here, and I'll have to scroll down a little bit. Let's put n to 2. With an n of 2, what happens? Well, this is the original distribution, and then the new distribution right here is the mean of 2 observations. So what are you watching? A sample of 2, and then a mean of those. Then you're watching a sample of 2, and then a mean of those. Then a sample of 2, and then a mean of it. Then a sample of 2, and then a mean. Who would have guessed that one would go right there? This distribution down here is not single observations. This distribution right here is the mean of a sample size of how many we chose. So I can't state this enough, that this is like talking to one person about their height, and then this is talking to how many people and doing what to their heights. This is talking to how many people and then doing what with their heights. This is like talking to how many people and doing what with their heights. This lower distribution, 2 and then averaging their heights, 10,000 points on zero right there. This is 2 people's heights averaged together. Because you take 2 random people and then you average their height. Watch as I can tell you where it's going to be. It's going to be right here. There we go. So the new one is going to be right there between it. I try to go as quick as I can. The next one's going to be right here because it's between it. It's just averaging them. So the new distribution will be more normal and tighter. That's tighter than the previous one. Let's turn this way higher. If we turn this up to 25, now every blue dot is what? Every single blue dot is what? Every single blue dot will be the what of what? Every single blue dot I get down there will be the what of what? Every single blue dot. Average of 25, 10,000 points. Amazing answers in the chat. Every single blue dot is the average of 25 observations. So I can make a bunch of blue dots like this and make a whole bunch, and that looks way wetter. When n got larger, that distribution got way wetter. It got way, way wetter. It's still normal, but it's way tighter. You're right. So this is the central limit theorem, that the distribution will become normal and more tighter. But there's a trick to it, and a really fun trick. Here's the trick, and I'm going to tell you it right now. Does everyone see that this standard deviation is 5? The formula, I'm jumping ahead a little bit in the notes. The formula for the mean is very easy. If you notice there, the mean for the distribution of the sample mean is equal to the mean. Well, what was the mean? Well, the mean was 16. So if the mean was 16, what is the distribution of the sample means mean? So the original mean, let me point to what I'm talking about. The original mean was 16. So if I run this down here, what will be the mean for the lower one? Well, if the original mean is 16, then the mean for this one will be 16. Does everyone see how it's right there at the same center? It has the same center. So the mean for the lower distribution is also the same because it's like, imagine if you were to talk to one guy and the average guy is 5'9", and if you talk to 100 guys, what would you expect the average height of 100 guys to be? Like if you took 100 guys and averaged them together, what would you expect the mean for 100 guys' heights to be? 5'9", 10,000 points right there, and all those answers of 16, 10,000 points. So does that make sense that if you were to average together 100 guys' heights, you'd expect it to be 5'9"? Because it's like saying, well, let's just average together 100 heights. Like, pretend there's 100 heights being averaged together, and you're like, well, if I average together 100 heights, I'd probably expect it to be about 16, and that's what the mean of the distribution would be. But here's the one that changes. The one that changes is this one right here. We have the standard deviation for the distribution of the sample mean. And that is the original standard deviation over the square root of n. And this is where this problem was a little bit nice to us. Because the original standard deviation was 5, and the new standard deviation is going to be divided by, go away, by square root of 25. And what will be the new standard deviation for the distribution of the sample mean? The new standard deviation for the distribution of the sample mean should be 1, 10,000 points right there. Julio, great job. It should be 1. I remember one's just like a line. That's a 1. And so we go here and we take a look, and let's see if that's true. Does everyone see how the original standard deviation was 5, and the new standard deviation is now 1? And think about this. As n gets larger, what happens in the equation? If n gets larger, this number down here will get water. If n gets larger, it just makes that the denominator in the equation bigger, and all of a sudden the standard deviation will get what? As n gets larger, then what happens to the standard deviation? It gets tighter, as in the standard deviation gets smaller, because the standard deviation controls the variation on the curve. So if you were to increase n, you'd get a tighter curve. It wouldn't change the center of the curve. The center is dictated by this right here, and that's not going to change, but the standard deviations will get tighter by a factor of square root of n. So you're basically making a tighter and tighter curve, because the only thing that changes about this curve is the standard deviation. This is a key concept right here. But here's the other concept. The other concept is the curve will actually become more normal. So let's go to a small sample size right here of only 2. Now, this distribution, as it says, is skewed. So let's take a look. Let's do 2 observations and average them together. Now, once again, the new distribution of the average of 2 values should be more normal and tighter. So, as we should, well, a lot of stuff to say there. So what we have right here is a tighter, more normal distribution. And yes, this is not normal enough yet. But what would happen? Tell me 2 things that will happen here if I increase n to 25. It'll become more what and what? If n goes to 25 and I do the average of 25 observations, that curve we just saw will become even more this and even more this. It'll become even more this and even more this. More normal and tighter, 10,000 points in the chat for everyone saying more normal and tighter. And so take a look. The new curve down here is this. And does that look normal? How does that look for normal? Exactly. It's more normal and tighter. And does that look pretty normal? It does to me. So that is what we need to do. This is what we need to understand right here, is that the central limit theorem is telling us that the curve will become more normal and tighter by a factor of the square root of n. But here's the biggest thing, and I've got some really great notes on this. So let's go find my notes. I bet it's this one right here. No, it's not that one. I can hover over them. That's Mr. T. We get to Mr. T today. Here we go. There it is. Okay. So I did this video yesterday where I went over some of these problems. And if you can see, we already have the formulas written out right here with showing how to use the mean for the distribution of the sample mean and the standard deviation for the distribution of the sample mean. Also, we have the large enough n condition, which is our third condition. Now, you'll notice some key things. Let me erase. I'm going to put new highlighting on here, so watch where I'm highlighting. If the distribution is already normal, how large does n need to be? If the distribution is already normal, n only needs to be what? If the distribution is already normal, n only needs to be 1. 10,000 points right there. If the distribution is skewed, n needs to be what? At least 25. If it's heavily skewed, it needs to be 100. I want you to notice something. 100,000 points, you know we're clicking that random button again, you know it. So first person to tell me, the more skewed it is, the water n needs to be. The more skewed it is, the water n needs to be. The more skewed it is, the water n needs to be. Yes, Zach got it first, Zach, and we're also going Zach and Braden, Elizabeth. Why not everyone down all the way to, why not everyone? So I love it. Keep answering those questions. That was a complete randomness right there. But the more skewed it is, the larger n needs to be. The more skewed it is, the larger n needs to be. Key stuff right there. So remember that. So if it's normal, how large does n need to be? Well, apparently n can be very small. It could be as small as 1. The applet doesn't let us choose that, but let's give it a shot. Let's go down here all the way, and let's pick an n of 2, and let's see right here. And then let's go right here, and let's go and do normal. And let's do this and see what happens. And is that normal? That is very normal right there. So even with an n of 2, we get a normal looking distribution right here, because why? Why is the distribution down low normal? Can anyone explain to me why is the distribution down low normal? Anyone have any ideas? Why is the new distribution of the mean normal? Why did that happen? Any ideas? Why is the distribution of the mean normal? Can you post a link to that? Yeah, of course. You got it. Thomas, 10,000 points. 100,000. Great question. It's a cool little applet. Because the top is normal. Abby, you are right. It's already normal. You got it. That is a link to it. Don't leave the whole thing. Check it out later. The parent distribution was already normal. You are totally right. Because it's close to, because it's already normal. Because the distribution is already normal. But let's say I had something ridiculously skewed. Then how large of a sample would we need if this is very, very skewed? If this right here is something that's extremely skewed, then would 25 be enough? Do you think 25 is enough? People are saying 100. You're probably right. And look, still skewed. You got it. Man, I wish I could. I miss being able to reach in the screen. We're going to be setting up new stuff. And when we get the Super Studio, which I'm really excited about, then just wait for it, because my hope is I'll literally have like a board I can go to and actually start writing on it. So get ready for a really awesome studio. And the more you guys like this and say it's a good way of teaching, the more we make this happen. So if you notice, this was not large enough. Does everyone understand that right here? That this was not large enough. So we do not have a large enough sample right here for it to actually work for the central limit theorem. Okay. Super Studio. You got it. Jack, I'm going to make you a mod right here. And we might start, I'll tell you guys in between the chapter. I'll give you guys some more updates on cool stuff. Lots of cool, fun stuff. Okay, so what we're seeing right here is the central limit theorem. Guess what? Any guesses on condition 1? I know it's on the screen, but I need to hear it from you guys. What is condition 1 for the central limit theorem? How do we get those observations? How in the world do I find those observations? Random. You are right. We must get those observations randomly, which means we randomly select observations. 10,000 points, all those randoms in the chat. What is condition number 2 for when we sample from the population? When we sample from the population, condition 2 says the sample size might be more than 10%. You're right, Snay, right there. Great answers in the chat. And then, let's see right here. The third condition is finally the one we were just talking about. It doesn't put 1 on there, but that's the confusing thing. And I say it because we've put it as a trick question on the test. I mean, I'm like, But if it's already normal, then you don't need a large sample size. So the third condition is called large enough. And you can always, here's the thing to know, that we always pause. Did anyone say pause? I was going to give 100,000 points. Someone said pause. I didn't see any pauses in there. But the way you know the third condition is ask yourself this. Pause, 10,000 points, 100,000, I said it. Zach got it. And Roderick got it. And Abby, and Justin. So we always pause because we have to ask ourselves what kind of data we're dealing with. If we have quantitative, then we will do the large enough n, which is large enough sample size. If we have categorical, what will the third condition be if it's categorical? If it is categorical, what will the third condition be? Any ideas on what the third condition will be if it's categorical? If it is categorical, like percent of students who like Taco Bell, the third condition will be what? And this is for categorical. Success, failure, Julio right there, 100,000 points, big points today. Thank you everyone for being here and participating. It'll be success, failure. But, and Audrey, 100,000 too, if we have the quantitative data, it's going to be large enough n condition. So we see all this right here. Does everyone have that written down? Categorical data, third condition is success, failure. Quantitative data, third condition is large enough n condition. This is a different chapter right now. Last but not least, you see some notes right here that they've given us that show us that the distribution is originally very skewed, and then the distribution will become more and more normal, more and more normal right here as the distribution goes to larger sample sizes. So each and every observation inside of here would be, that's more than one observation, but it'd be the average of 100 observations. So this is the average of 100 observations right here. So make sure you know that this is not the original distribution. This is like taking 100 different observations from this parent population and averaging them together. So very, very, very important concepts right there. But this concept, if you're wondering why I'm going through these slides quickly, this is what I'm talking about here. That we have right here 25 observations from a very skewed distribution. Once again, why is this not normal? If it's very skewed, how large does the large enough n conditions say we need of a sample size to make the distribution of the mean normal? To make the distribution of the mean 100, yep. And there is a caveat that let's say it's extremely, extremely skewed. Well, then you might need 200. Now, we don't do that in Tool 1, but it can always be more and more skewed. So you could say, what if it's super skewed? You're like, well, then maybe you need 200. But the thing is the more skewed it is, the wider n needs to be. The more skewed it is, the wider n needs to be. Because think, 1 if it's normal, 25 if it's skewed, 100, there you go, Snare, right? You're right. Third condition categorical is success failure, you're right. The bigger, the larger it needs to be. And so we see here, if we only do a sample size of like 2 here, then the distribution will look not normal at all. But if you notice as I bring this up higher, you're going to see it get more and more normal. And you see that looks more normal. And then at 25, it starts to look pretty normal, but not normal enough. We probably need like 100. So key, great concepts there. Excellent work. Quantitative condition, yes, large enough n. Abby, 100,000 points. Okay, so here's a good bit of review from last chapter. We have right here that the mean for the distribution of the sample proportion is equal to the true proportion. This is like saying 70% of UT students like Taco Bell. Well, if I took a sample of students, I'd expect to see in my sample 70% of them liking Taco Bell. Next, we see here that the mean for the distribution of the sample mean is equal to the mean. I start off on the wrong side. The mean for the distribution of the sample mean is equal to the mean. So that's like saying if the average guy's height at UT is 5'9", then if I took a sample of guys, I'd expect to see in that sample 5'9". Let me highlight those words as I say it. If the average guy's height at UT is 5'9", like that's the true mean, then if I took a sample of guys, I'd expect to see in my sample 5'9" as the mean. So you'd expect to see a sample mean of this. The other one is the true proportion, like 70% of students like Taco Bell. Well, if I took a sample proportion, I'd expect to see in my sample proportion 70%. So that's what we have right there. Excellent work on that. Does everyone understand the notation on this? It's just the center of your distribution. And do you know how to read this? Once again, read this one on the left as what you expect to see when you take a sample, like your expected sample proportion, what you expect to see for your sample mean. What do you expect to see for your sample mean? What is the expected sample mean that you are going to get? What sample mean do you expect to get? The sample mean that's most likely to get would be the what? Who knows for 100,000 points? Close. Abby, I'll take that for 100,000, but I want more specific. We'll be very specific. Everyone's saying the mean, but I want really specific. The true mean, you're right, Julio got 100,000. The true mean, also Elizabeth. The true mean. So if you were to take a sample proportion, what would you expect to see for the sample proportion? What do you expect to see if you take a sample proportion? What's the most likely thing to see if you take a sample proportion? What would you expect to see with the sample proportion? The true proportion. Exactly. You'd expect to see the true proportion. Exactly. Okay. So here we go to the last bit of the formulas. These are things we already know, because we already know the standard deviation for the sample proportion is going to be P times Q over N square root. P times Q over N square root. And all this tells us is the standard deviation on the curve. Like if we draw out a curve here, the mean is at the center, and then the standard deviations are these little tick marks going up and down, 3 standard deviations above and below. So these are the standard deviations right here, and this is how we find them. So this one, you'll notice we were doing this formula earlier, is just going to be sigma over square root of n. Sigma over square root of n is how it gets tighter. So remember, sigma over square root of n is taking your original standard deviation and dividing it by the square root of n. Now remember, you do get formula sheets. These formulas look very similar, but remember, we should know every bit of notation right here. We should know that this reads, the standard deviation for the sample proportion is the true proportion times its complement over the sample size. The standard deviation for the distribution of the sample mean is the true standard deviation, that's what sigma is, it's the truth for everybody, times the square root of n, or excuse me, over the square root of n. So we have that right there. And let's continue on. There's the applet I think I was using, and we have an example problem. Now, so one key thing right here, I'm not going to work the example problem because we're going to make sure we get kind of to the end of today's lecture and we've got conference rules to talk about, but I want to point out something. The best example problem, and this is how I want to best utilize time right now, is, let me show you where you can really get some good help. But you can't, it's a YouTube channel, maybe you've heard of it. Self-promotion at its worst. This video right here that we just did, oops, wrong screen. There we go. Okay, so this video right here, if you notice, go in right here. Where are we going? There we are. So let's go right here, and you'll notice I work an example problem in this one right here. This is the formula sheet you're seeing from what I was doing. I'm showing you how the applet works, and I do this whole problem. So I also liked my own video, so you gotta do what you can. You gotta, I mean, if it lets me hit like, I'm gonna hit like on my own video. So there we go. With this problem right here, I'm sure someone else noticed, like, hey, you've liked your own video. So I didn't, maybe I should just go in here and hit unlike, right? There we go. So with this right here, I don't think I've liked everyone. Spam likes. Thank you guys so much. If you're, especially when we get monetized, it'll help out. Once again, all money from the channel will go to students. That's my goal. It's like, so no, don't bot. We will never, ever, ever, ever bot. But I will ask you guys to like videos. I won't be like, please like the video, but I'll ask. I'll be like, hey, if you want to like the video, like the video. So this problem right here, I go through all the examples of how to solve it, and I also do the carbon monoxide problem. So for people who want to do these problems, like, comment, subscribe, yep, ring that bell. So has anyone been doing the homework problems and is stuck on any of these? We mentioned it earlier, but I work through both the waiter-waitress problem and I work through and I explain how to do all of them. I go through the concepts again. You can see people in the chat right there. And then I did some other review of other stuff, talking about how to find probabilities and stuff. Where can you find these videos? Here, I'll put it in the chat. They're all on the YouTube channel. They're all public right now. And so this video is right here. Don't leave this video completely yet. But all these videos right here can be found on the channel, and we're going to try to I'll probably try to go in and put timestamps in them. If you want to put timestamps in the video, that helps me a lot. Like if you're like, Brian starts doing this problem at this time, you can put it in the comments. You guys know I love your comments, and please also put comments on as many of you, don't spam comments, but put comments like, I learned this, or at this time Brian did this and taught me this. That really helps. A lot of people use comments a lot, and I'm trying to keep up and respond to them. But after a video is done, add comments. It really helps the algorithm think that I hope we're making good content. So that's got that, but that's the example problem, and I'll be doing a lot more office hours. We're doing a Kahoot tomorrow. So we're going to do a lot of stuff where you can talk to me and we can work problems. So that's why I skipped the example problem here. So there's an example problem, but still, don't worry. And I think it's in the other video I do the example problem. But I guess the other big thing is we're going to try to stream on Twitch. Does anyone know much about Twitch? I'm using this as a 2-minute break right here. Does anyone know anything about Twitch? Ever heard this channel called Twitch? It looks like a no. No one's ever heard of Twitch. So, no, Zach's never heard of it. Dang it, darn Zach. They're saying yep. So I'm gonna try to heard of it. So one cool thing about Twitch is it's mainly a gaming platform, but I'm gonna try to pro gamer, yeah. And so I'm gonna try to stream on Twitch. We'll do some. Would it be crazy? I was doing Fortnite. I don't know, if I get bored enough, I might try Fortnite. But Twitch will be. Is there a dancer named Twitch? So Twitch will be. We'll try to do some streams, but also if you have Amazon Prime, you can do Twitch Prime. It's totally free for the people doing that. I'm not playing nearly any Pokemon Go anymore because I'm not going outside much. Yeah, I'll tell you what. I thought about this. Logan asked a really good question. If I thought about making goals for how many people we could have, because here's the crazy thing. If if you have Amazon Prime, you can do Twitch Prime for free, and you can give one streamer your Twitch Prime. Now, you can give whatever streamer you want that Twitch Prime, but everyone's saying Animal Crossing, good game right there. I've heard the new one's pretty awesome. But if you give that streamer your Amazon Prime, they make like $2 or $3 that month, and it's totally free for you. But imagine if like all of UT students were to, and they can give whoever they want it, but we'd put that money back in. So we're going to try to, I like that emoji right there, Abigail. So we're going to try to, you know, I don't know, maybe stream on Twitch. I want to see Brian stream Fortnite. I've played some FPS. So, but the hardest thing about Fortnite, I've watched people like Ninja play that game, and like when they build and stuff and they just swing around and they like build something around themselves, it's 2 games in one. It's building and FPS. So I don't know how good I'd be at it. And especially right now with me starting this late, I'd be destroyed. I did play Minecraft back in the day. So I played some Minecraft. I can beat Super Mario 1 in under 7 minutes. I used to play, I was really good at 1 FPS. I was really good at, no, it was a second. It was like an over the shoulder. It was, it's the last little aside here. Transformers, War on Cybertron. I think it was War on Cybertron. It was a really great game, the Transformers game. People would say I was cheating stuff. I was so good at it. I know it's like you're like, no, really? And like, yeah, I got people like sending me messages on Xbox Live being like, you're cheating. And I'm like, no. And they're like, how'd you do this? And I'm like, I play the game all the time. Statue and Minecraft server. We could, Ocarina of Time. I still need to beat Ocarina of Time. Mario Sunshine, good games right there. Okay. Oh, here we go. You have Minecraft on your TV. It's, man, maybe I'll, you know what I could do if we start getting subs, maybe I'll show off my Minecraft world. I have a shrine to Captain Planet in my Minecraft world. Xbox chat, yeah. Okay, awesome. You guys ready? We got our break in. You guys ready for some conference rolls now? So you second the random button. Oh, there'll be a random button again throughout class. So okay, we'll start today off with some randomness right here. I want people to tell me what is at the center of a confidence interval for the mean. A confidence interval for the mean, 100,000 points. What is at the center of it? What is at the center of the confidence interval for the mean? Any ideas? Nope. 100,000 points. Nope. Nope. What is at the center for the confidence interval for the mean? Nope. Nope. Oh, Caleb got it. Caleb got it right there. Caleb is right. Let's look at that formula again. Nice job, Caleb, right there. We're back into learning again. We had our little bit of break in there. Y bar plus or minus T star n minus 1 s over square root of n. Just remember it in parts. The best way to memorize stuff is by chunking. You've got your center. You've got your margin of error, and the margin of error has 2 parts. The T tells you your confidence level, and the last part is the standard error. So very important that you know all the things right there. But we're going to talk about some very special people today. And first, very special person 1 is going to be, I got to pull up his picture right here. So let's bring up very special person 1 who had a hand in making this interval right here. Very special person 1 is going to be, if I can go up to my other screen and take a picture of it. You guessed it. It is Mr. T. Mr. T right here created the T interval. He did something very important. He time traveled. Be very careful when you time travel. But Mr. T created the T interval. I've still got my picture up from last class, don't I? There we go. Here we go. Here's the T interval Mr. T created. He took the Z curve. He said, I'll pay the fool, and smashed down. Yes, if someone doesn't know Mr. T, you got to know Mr. T. So Mr. T took the curve and smashed it down. Bring Mr. T in here. So, whoop. He is such a cool dude. I still have a dream of meeting Mr. T. Hopefully it happens one of these days. Go behind text. Mr. T, he's up here. And there's his fist. He's got space pen. It does look like a foot, doesn't it? Mr. T came in and he smashed down this curve. So I want us to look at the T curve. And I want us to remember something about the T curve. The T curve is basically just the what curve. The T curve is almost exactly like the what curve. The T curve is almost exactly... The T curve is... I'll look it up after class. The t-curve is almost exactly like the z-curve. You are exactly right. What is the difference between the t and the z-curve? So this dude is not nearly as cool as Mr. T. I gotta go take his picture now. Well, no, we'll take this thing over here. All right. So this guy is the actual guy who made the t-curve. So I gotta bring his picture down. This is the actual dude who made the t-curve. But he did do something kind of cool. It's not nearly as cool as Mr. T. I'm actually older than him in that picture. I looked it up last time and I was like, holy crap. This guy right here is William Gossett. So William Gossett actually made the t-curve. He worked at Guinness Beer. So there's his thing, his little plaque at Guinness Beer. Sorry, I'm away from the microphone. And so if you can't read this, or I'll make it, well, it says William Gossett. It's got his like years, and it says Chief Brewer. Probably was really quiet there. But William Gossett is the actual one who made this curve right here. So he did look pretty good there. That was a pretty good picture. He doesn't look as good as Mr. T. But I've actually had seniors in statistics tell me they remember the T-curve because it's just the Z-curve but flattened down. You don't believe me? You're like, Brian, you're making stuff up. You're just telling us weird stories because that's what you do. Well, watch. The T has with it degrees of freedom. So Mr. T will smash down the curve. Zach doesn't believe me. He'll smash down the curve, and then he'll give it degrees of freedom by letting off the curve. Does everyone understand that? Mr. T smashes down the curve, and then he gives it degrees of freedom so it can be normal. So a T-curve with 1 degree of freedom, does it have a lot of degrees of freedom to be normal? Yes or no? With 1 degree of freedom, does that sound like a lot of degrees of freedom to be normal? Does that sound like a lot of degrees of freedom to be normal, a T-curve with 1 degree of freedom? No, not at all. And look at it. It's smashed down. He came in and smashed down the curve. But as he gives it more freedom, what's the curve doing? 10,000 points, all those answers. What's the curve doing as I give it more freedom here? It's becoming more and more what? More and more what? Normal. Not, well, kind of tighter too, but normal. It's becoming more normal. Remember, what we just saw earlier is that the T-curve is basically the Z-curve smashed down, but it has with it this thing called degrees of freedom. This is a huge concept, that the T-curve has in it degrees of freedom, and the more freedom it has, the more normal it can be. What is the Z-score for a 95% confidence interval? Does anyone know? 100,000 points, complete random here. 100,000 points. What is the Z-score for a 95% confidence interval? I want to know exactly what the Z-score is. First person who's got it. Z-score for a 90. Zach, that's close. Zach, you get 10,000. Julio is right. It's 1.96. It's actually on the screen. It's 1.96. Wait a minute. This is the T-score. Because what does the T-curve do as it gets more degrees of freedom? It turns into the what? It approaches and becomes very close to the what? The normal curve. So 2 is very close, but 1.96 is the exact. But watch this. What if this T-curve only has 4 degrees of freedom? With 4 degrees of freedom, what is the T-score for a 95% confidence interval? With 4 degrees of freedom, what is the T-score for a 95% confidence interval? With 4 degrees of freedom, William, you're exact. William, 100,000 points. A great answer right there from William. I'm trying to call out many people I can see. You are correct. 10,000 points if you got the answer right here. This is the T-score for a 95% confidence interval. Sorry, the one thing's off the screen. But 95% confidence with 4 degrees of freedom. So what must you ask somebody whenever, what is Z and normal? Are they interchangeable? The Z curve is what we use for normal confidence intervals, like when you know the standard deviation. And what was the other thing? What is the Z curve and what is, let me review the question. Z's come from the normal curve. Calissa, great question. The Z curve, and we can look at that real quickly here. The normal curve, everything on here is a Z score. So whenever I say a Z-score, it comes from the normal curve. So those are completely interchangeable. If I say, oh, the thing on the normal curve, and it does have a mean standard deviation of 1 if it's a Z-score, and then I say it's a Z-score must come from the normal curve, and then a T-score comes from the what curve? A T-score comes from the what curve? Keep asking questions, Abby. Don't worry. This is a big concept. I'm glad people are saying they're confused because that means you have questions to ask. T-scores come from the T-curve. And so William Gossett created this curve right here that is basically the normal curve. The t-curve has with it degrees of freedom. So there are as many t-curves as there are degrees of freedom that you can input. I think you can even input decimals. Sometimes they'll accept it, some applets will or some won't. So the higher the value of freedom means it's more like the z-curve. Yes, Alexander, you are right. After a certain point, it's really just negligible because look at that right there. It's negligible. It's like, well, it's basically the same thing. And if you were to go down in degrees of freedom, look now it's 1.984. So now it's very close to 1.986, or 1.96, excuse me, but it's not quite the z-score. So z's and t's are virtually identical. But you might be wondering why he did this. It's so crazy. And I think about this story of, you got it, Simon, 10,000 points. Simon, you are right. I'll get to that in a moment. But whoops, hit the microphone. Simon, you are exactly right. Z's come from a normal curve. Where do t's come from? T's come from the t-curve. So t's come from the student t distribution. The craziest thing is this, is William Gossett, this guy right here, was having a feud. This guy up there was having a feud with a guy, at least what I've heard, Ronald Fisher, that's his name, another famous statistician. And he wouldn't publish William Gossett's work. So he called his work the student t distribution. You can see it down here. He called it the student t distribution, and he worked at Guinness beer. So imagine this guy right here drinking beer and coming up with distributions and just like making mathematics. And then people are like, you're just like a brewer at a beer company. We're not going to accept your work. And then he came up with a fake name, a pseudonym, and they accepted his work, and it got published, and it changed the world of statistics. The t-curve is a more accurate way of calculating your confidence intervals. So thank you to Mr. T and William Gossett, because we have this more accurate way of making curves which account for the small sample sizes and include extra variation. Now that's extra stuff. That's extra knowledge right there, and we need to understand just that when we use the t-curve, we're calculating usually confidence intervals for the mean, or we're doing t-tests. Are there still questions? Everyone's a little bit silent right now. But the t-curve is used to make confidence intervals for the mean or to do tests on the mean, all that good stuff right there. And it's basically the z-curve. So I like for you to understand it this way because the t-curve is basically the z-curve. But what must you know whenever you do the t distribution? What must you know whenever you do the t distribution? 100,000 points first person in the chat, 10,000 points everyone else. What must you know whenever you're doing the t distribution? To know what t you're using, you must know the what. To know what t you're using, you must know the degrees of freedom. Yes, you are right. n-1 for this one, which is the degrees of freedom. So let's talk about that right here because people wonder, well, how do I find the degrees of freedom? And let's review just briefly. So you would think you would make a 95% confidence roll using the standard deviation and 1.96. But what I've highlighted right here, right now, is the standard deviation for everything. This is the total standard deviation of all the data. If we don't have that, we have to use S. But now we can't use 1.96 because 1.96 is for the z-score. We don't use z-scores anymore, we use a t-score. So that's where William Gossett came in the 1800s or so, late 1800s, and he created the t distribution called the student t. Once again, William Gossett created it, and then there's another picture of him right there, and he used the fake name on it. Every t has degrees of freedom. So what are the degrees of freedom for this one? Well, it's as simple as n-1. I was trying to show it. There it is right there. The degrees of freedom for a one sample t distribution. The degrees of freedom for a one sample are n-1. So t, I like it, right, Jake? 10,000 points, 100,000, why not? I like all the jokes in the chat. The t distribution has with it degrees of freedom. It gets degrees. T's get degrees. I might start using that. Jake, I'm throwing you 500,000 points. I really like that. I might start saying that from later semester. Remember, T's get degrees. I really like that. You well earned that 500,000 points. Great thing in the chat. Yeah, that's an amazing. I like that's how we learn. Is you remember T's get degrees. So he earned it. That was an amazing comment right there. That was an amazing comment. And I love all the comments, but when I'm like, I might start using that for the remainder of like when I teach these. I always teach these topics. I really like T's get degrees. So everyone, I love the chat. Oh man, you know what that was. That was just It's just completely, today's class is completely brought to you by randomness. The economy is ruined. So keep up the great work, everyone. Keep the comments coming. Okay, so let's continue on here. We're almost done with today's lecture. Thank you so much for your attention, and thank you for staying involved in the chat. Remember, we're here to have fun, and we're here to learn. Which of these two distributions, the higher one or the shorter one, is normal? Don't look at the answers. Which one, the higher one or the lower one, is normal? The lower one or the higher one? By one sample. Oh, yeah, Snag, great question. One sample means we talk to UT students. Two samples means we talk to UT and Florida students. So two sample would be, we took samples from UT and Florida students. The normal will be the higher one. You can probably see through it. And the T is the smash down one. I pay the fool. So one sample is, I talk to UT students. Two samples is, I talk to UT students and Florida students, like 50 UT students, 30 Florida students. So there'd be two sample sizes. One sample would be, I talk to my friends. Two samples would be, I talk to my friends and my brother's friends. But then I'm treating them as two samples. Like I talk to 10 of my friends and 10 of my brother's friends. So then we have two samples here. My friends is one sample. My brother's friends is two samples. That's a two sample right there. Great question. Whenever you see something you don't know, ask it and I will answer it. So, great job. And they both do look normal. Simon, 10,000 points right there. Simon, you're right. They both look pretty normal, but remember, the T is smashed down. So you can tell which one the T is because it's smashed down. The T is always lower than the normal. Even if it has like a million degrees of freedom, it would just be so close to the normal that it'd basically be the normal. Condition 1. We got to see it in the chat. Condition 1. Anyone have any ideas for condition 1? Condition 1. What is it? Oh, they're not always shown together, Calissa, great question. It's just we're kind of comparing them. So we only use the normal when we know the true standard deviation, and we use the T when we know the sample standard deviation. So the T is often used for means. The T is used for means, and I'll maybe talk more on that in a moment. But condition 1 is random, and that means we have randomly collected our observations. Condition 2 is 10%. You guys know that. And then what do we do? What do we do before condition 3? What do we do before condition 3? You guys know it. Guys and gals, you're welcome, Calissa. Ask any question you have. We pause. We pause for 10,000 points right there. We pause and we make sure that we stop and we think what kind of data it is. I'm doing the mean. So will it be large enough, which we can still call it that. Don't worry, it's going to say something different on the next slide. But it will be large enough, I've already given it away, or will it be success failure? Will it be large enough or will it be success failure? Which will it be? Because it's the mean. We're not doing categorical anymore. Will it be large enough or will it be success failure? It'll be large enough. Now, it is calling it nearly normal right here, but you can still use the sample sizes. And please remember that I like the numbers 1, 25, and 100. For some reason, in the notes, they like changing the numbers, but still it works that the larger it is, the more normal it is. We talked about this a long time ago in 201, and we're like, well, it's still basically the large enough n condition because it's your sample size. The larger the sample size is, the more normal the distribution will be. Now, I want everyone to tell me, I'm going to redraw this down here, even though I drew it one time. If I have a distribution that is skewed, and I have a sample size of 200, do I pass the third condition here? I have a sample that is skewed, or even very skewed, and I have a sample size of 200. Do I pass the third condition? You're right, yes, I do. Because if the distribution is skewed, I need a sample size of at least 100, and then the distribution of the mean will be more normal and tighter. And that's what that next slide is getting at. The distribution of the mean, yep, because n is large enough. That's exactly it. What if my original distribution, which is what this slide is talking about, is normal? Like, let's say my original distribution is pretty darn normal. Like, it looks like this. Then can I do it? I mean, let's say the sample size is 5. I'm going to do the mean of 5. Can I do it? Yep. Oops, you can't see that's off the screen. Yep, I can totally, we'll go over here. I can totally still do that with an n of 5. So yeah, nice and easy right there. We can totally still do that. Perfect. That is what it's talking about right there. Here is the formula, and we have just enough time. Literally, it's so funny. I get to the same spots with every class. So here is the formula. So the bigger the number, the more skewed the curve. But kind of. So here's the steps. You ready for it? Elizabeth, great question. 100,000 points, Elizabeth. Here's what you have to do. Whenever you are given a problem, you must look at step 1. Let's put steps for testing nearly normal. So large enough steps. step one is to look at the distribution. So we might see something like this right here. You need to look at it. And this is very skewed. So step one is to look at the distribution. Does everyone see that? We're just going to just look at it. Step two is a number for this. So we need to know the number. Oops, it's not an E. So we need to know the number for this shape. And then step three is am I going? Okay, good. One of these days I'll learn how to write better. Okay, so let's look at this right here. Someone tell me, let's pretend we're going to do a mean for how many push-ups people can do, a very skewed distribution. So this distribution is very skewed, and we take a sample of 150 people. Pretty much this is maybe a little better laid out right here, and so this will maybe help people better understand. It's same concept, but I'm trying to put it in a hopefully easy to understand way. So if we are taking the mean of 150 people, and we want to figure out the true mean, do we pass the large enough n condition right here? And why do we pass it? Well, this is very skewed. Does everyone see how this distribution is very skewed? So how much do we need for the shape very skewed? For very skewed, we need at least what? We need at least 100. So then we know we need 100 for this, and then we pass because our sample size is 150. Does that make sense right there? Now let's do it again right here. And let's say we're only doing a very small sample. Like let's say, and this happens a lot in research, you know historically that people's metabolisms are normally distributed and you only have enough money to get 12 samples. So this is very normal right here. Metabolisms are normally distributed and you only have enough money to get 12 samples. Do you pass the large enough n condition right here with only 12 samples? Would you be able to do you pass the large enough n / nearly normal condition with 12 samples? People are saying yes in the chat. Yes, because the rule for this shape is 1, and then we have 12, which means we pass. If it's already normal, you're good, so you don't need a large sample size. So you're very good on that. That passes. And then we'll do the last shape right here, which is kind of skewed. So if it's kind of skewed, and we'll do a counterexample here. I'm going to call this skewed, just like regular skewed. And so now it's skewed, not very skewed. And now you're still doing just a sample size of 12. See, SBN. So now you do a sample size of 12 again. Do we pass when this one's kind of skewed? Be careful. This one's skewed. This one's just skewed. So this one's only skewed, 10,000 points still though. So no, you do not pass because we have 12. Wait. Number for the shape. I hope I put it in the right spot. 25, yeah. This is 25 we need for the shape, and then we only have 12. We do not pass. Does everyone understand? These are the steps you can do. First thing you need to do is look at the shape, and then you need to remember the amount you need for that shape, and then you need to ask yourself, do I have that amount? So we need at least 25. Does that make sense on these steps? Yes! Elizabeth, that's what I like seeing. Thank you for the question. You need at least 25. We do not Abby, 100,000 points, Abby. Great answer in the chat. So remember, for these great answers, when you write out like that, I wish it was a written test, because Abby, the way you wrote that is the exact answer we would want you to write on the test. That is literally the answer for why do we pass the condition or not. The last thing I want to talk about here is where people make mistakes. And actually, we should have enough time, because literally we're tracking the same time as the last class. So what do we have right here? We have a problem right here where we find a confidence interval for the speed of cars on Triphammer Road. So we have right here that we want to make a 90% confidence interval. What does 90% tell us? It tells us the t we need to find. And then 23 is the sample size. So 93, I might erase notes next time or pull new notes up. I don't know if I like having the notes up already. 23 is the sample size. And then from the sample size, how in the world do we find the degrees of freedom? The complicated formula for a one sample degrees of freedom is n minus 1. So the degrees of freedom here are 22. I want to see this in the chat. 100,000 points for one of our, we're not done yet, but I want to see in the chat, what do the degrees of freedom tell you? And first person gets 200,000, second, everyone else gets 100,000, but what do the degrees of freedom tell you? What do the degrees of freedom tell you? You need to know this. Why do remember T's get degrees? So what does that mean? What does T's get degrees mean? People yell out, kind of, Jacob, kind of close like that. Kind of. It's, don't worry, everyone's getting 100,000 who's answering. I'm going to be very specific on this. The degrees of freedom tell us, it is true, the more degrees of freedom, the closer it is to the normal. Abigail, Abigail's pretty much saying what everyone's telling, but I like the answer the best. Abigail, I'm going to give you the points because we're getting to the end of class. The degrees of freedom tell us the shape of the T-curve. So you literally have to go to a T-applet and put in 22 degrees of freedom. We're going to make a confidence interval on this, and then we're going to put in 90% confidence interval, and there's the T-score. Did everyone see how I found the T-score? Did everyone see how I found it? I had to put in the degrees of freedom, which will change the shape of the curve, and it does become more normal as this goes up, but it's 22 degrees of freedom, which tells me the shape of the T-curve. So every T-curve is based on the degrees of freedom, which control the shape. So the degrees of freedom show the shape of the T-curve, and the higher the degrees of freedom, the more normal it is. I'm assuming this would, yes, we would definitely have to give this to. Great job. Or we could show you pictures of stuff. Once again, trying to make this as fair as possible of a test. And let's hop back to here. And last but not least, we see the problem worked. Here's the thing. Once we get that T-curve, and let me point this out. Does this curve right here look very normal to everyone? Yes or no? Does that curve look very normal? We would give you the numbers. It's very hard for us to do it on the test without just giving it to you. Or conceptually, we can ask you questions. Since that looks very normal, is a sample size of 23 large enough? Remember, this looks very normal, so is a sample size of 23 large enough? It looks pretty normal to me. Yes, because basically 1 would be good enough. So since this is basically normal, we're good enough. So sample size really doesn't matter. Last but not least, we get the formula, and I've got these numbers in my head. So let's do the formula again, or I'll go down to here we are right here, to the final thing where I ended class last time. Take a look right here, that at the center of your interval is the sample mean. This is the speed at which people were traveling on Triphammer Road. Then we have plus or minus, which is the margin of error. Next, we have 1.717, which is the T-score we found. Remember, you do not multiply by n minus 1. Do not do that. The star means you get to pick it, and the degrees of freedom tell you the shape. So I had to go to my applet. I had to put in here that this is 22. Now, do not multiply by 22. I've seen a lot of students do that. But it's 22 degrees of freedom because the sample size was 23. And then you have to go to the applet and literally put in to the applet. Let's hop back to that applet. And you have to put in here 22 degrees of freedom with a 90% shaded in the middle. So we see that nice and neat right there. Last but not least, we have the standard deviation of cars on Triphammer Road. And there it is right there. That's S. We have the sample size, square rooted, and that is the standard error. The value of S will be given to you, definitely. So for N, we plug in the degrees of freedom. Let me show right here. This would be, maybe one of these days I'll change this to make it, there we go. This is 23 right here, but that solves to 22. So the degrees of freedom are 22. Nice job, Julio and Chad, 10,000 points. And then we would get the interval 29.47 to 32.52. And that is a 95% confidence interval for the true mean speed of cars on Triphammer Road that day. It's pretty much just reading through what we give you, and we would say, I am 95% confident the true mean speed of cars on Triphammer Road that day is contained in the interval 29.52 to 32.56. Oh, 90%. Julio, 100,000 points right there. Thank you for the correction. 90% because it's what the problem wanted. Marina right there, 100,000 points also. But I'll have to check out everyone's Minecraft servers, so maybe I'll start playing Minecraft again, who knows. But good job having you. We're pretty much done right now. It's just kind of, we'll talk about a little more next time, but if you have questions, feel free to ask. Great job. I think, where did you get the 90% from? The problem stated we want to make a 90% confidence interval, so the problem told us make it 90%. Yes, Abby, great answer, 10,000 points. You are correct. You plug in your sample size minus 1, stream. I'd have to put Minecraft on this computer. I don't know. Maybe I'll get bored and just be like, yeah, I'm just going to stream Minecraft when I'm not doing anything. Who knows? So that's got it right there. Stream Minecraft. Minecraft is fun, but it's my friend Cody and I would play it some. It's one of those games you can play for like 3 hours, and then you're like, you look up and you're like, what did I do for 3 hours? it's fun to play it in like, there's a guy, this is my last little ramble. Did you have to find the standard deviation will be given to you? Can you update the where's brought? Yes, Thomas, totally. Great advice. I'm going to figure out a schedule for myself to stream. So I'll update that this weekend probably. So Thomas, thank you so much for asking that. 100,000 points, Thomas. That's on my agenda to get done. Getting the studio set up was one to make sure I can do everything. And so I'm really glad. First stream we did today crashed for some random reason. And I was like, oh no, but then everything's worked fine after that. And yes, and I had to get my internet updated. People heard about that in the previous streams. So for the test, we have to print a formula sheet, correct? Yes, if you can't print it, you can write it down. Just make sure you show it. Can you explain the pass-fail? The success-failure condition? Yep. I'll keep going here. We're done right now, but I can do old material or explain stuff. I'll be posting the formula sheet. We went through it yesterday, so I'll be posting it and sending it out and sending lots of updates, especially like Friday, Saturday, Sunday about the test, so where you can take a practice test and all that good stuff. The success-failure condition is the third condition for categorical variables. So when you do the success-failure condition, we have two versions of it we use right now. We do P or NP. So it's NP and NQ need to be greater than or equal to 10, or it's NP hat, NQ hat needs to be greater than or equal to 10, and later on it'll be NP naught or NQ naught is greater than or equal to 10. So this one right here is for sampling. This one is confidence intervals, and this one is tests. This is the total extent of this success-failure condition. The top one right here would be a question such as like, we go out and sample 100 students and we want to find out what's the probability of finding 80% or more of students liking Taco Bell where 70% of students like Taco Bell. If you notice, we know the truth in this problem. I did it really quickly, but 70% of students like Taco Bell. Well, if I tell you 70% of students like Taco Bell, you know P. So it's basically like if you know P, you'll use P. So when we know the truth, we use NP, NQ. In the sampling problem, we're saying we know 70% of students like Taco Bell. I don't know how anyone would know that, but it's the truth, so we'd use the truth. Now, when we do a confidence interval, what's our best guess of the truth? It's P hat. This would be like we went out and spoke to 100 students and 70 of them like Taco Bell. Now, interestingly enough, if 70 students like Taco Bell, that's actually NP hat. So we would get NP hat right here is 70 because 70% of 100 or 70 out of 100. Then NQ hat would be 30. And also in my previous example, if I say I know 70% of students like Taco Bell, then if I spoke to 100 students, I would expect 70 of them to like Taco Bell. I can change the numbers here briefly, like if 60% of students have taken Stat 201 in Haslam College of Business, and I talk to 200 students, well, then this would equal 120, and this would equal 80. Because n in this problem is 200, we'll do that in space pen, and then p was 0.60, and I'm just making up these numbers. So 60% of students have taken Stat 201, and we just know that that's like a known thing. It's not saying in a sample 60% have taken Stat 201, it's saying I know 60% of students have taken Stat 201. When you go down to the next problem, it changes though. The next problem would be I spoke to 200 students, and 60% of them have taken Stat 201. So now the 120 here is the amount in the sample that said yes. Now notice this one right here is 120, and that makes this 80. If you notice, NP hat and NQ hat, or all of these, have to add up to n. So it's just saying in my sample I observed 120 students. Then when you do tests, it's actually via the hypothesized, which we haven't done yet. We'll do that later on. But you could say, we want to see if it's true that more than 50% of students have taken Stat 201. And so now, if you sample 200 students, you'd use the hypothesized 50% right here. And both of these would equal 100, because Q naught would equal 100 also. So there's small differences right here between these. P naught is what we hypothesize the proportion to be. P hat is the proportion we observe in a sample. And P is the proportion for the true population. Does that help right there with the success-failure condition, Logan? That is the success-failure condition. If anyone else says, you can write the formulas on the sheet as they're saying in the chat. But if you have a printer, please print it. It'll just be easier because you're going to be holding up a sheet, and probably easier to just print it and all that good stuff right there. Any other last few questions that anyone has That helped out? Good, good, good. If you understood this completely, you understand the success failure condition at the highest level we can teach it to you at. But knowing what sample size is, so once again, let me highlight all the words, or highlight the things as I talk about them. So here we have sample size, here we have true proportion, here we have complement of that. These are just like if that's 0.8, the other one's 0.2. And then here we have sample size, sample proportion, which means it comes from a sample, and then complement of that sample proportion right there. Here we have sample size again, and then we have hypothesized true proportion, which means we're saying, well, let's hypothesize that 50% is the true proportion. So we're just making a guess at it, basically. And then here's the complement. So if it's 0.5 for P naught, it's 0.5 for Q naught. P naught and Q naught are complements, just like P hat, Q hat, and PQ. That's got it. Any other last questions? Did you guys enjoy chat? Did you guys enjoy class? Hopefully everyone had a great time. Maybe we only have like 2 people watching now. We'll find out. But thank you everyone for being here. If you have any last questions, feel free to ask. So good having everyone here. Good stuff today. A lot of streaming. You're welcome, Jake. So good to see everyone. Keep showing up. We've got a lot of people in class, so hopefully everyone shows up. But I'm so glad to see everyone. And feel free to say bye in the chat. 10,000 points if you say bye. Why not? 10,000 points, say bye. You're still here, just following along. Say bye in the chat. We'll say bye, everyone. Tag someone if you want. Bye, Jake. Bye, Sophie, everyone. Okay, well, cool. I might have a bunch of people. Bye, see everyone. Bye, Thomas. Bye, Kaylee. Bye, Calissa. Awesome stuff. I appreciate you guys. We might be doing more streaming later. Who knows? Horatio, good to see you. Joelle, good to see you. Kaylee. Were they in, Kaylee, were they in my actual class? What class were they in? Or who is it? Did they take my class before? See who it was. Which student is it? Because I'm wondering who it was now. Bye, everybody. It's like, here, people. Oh, that's, this is my last little aside. Someone's mom, last semester was walking through campus and they stopped and they're like, "Are you Brian Stevens?" And I was like, "Yeah." And they were like, I was like, "Yeah?" And they were like, "I'm so-and-so's mom. I listen to you all the time on the internet when you're teaching class." And I was like, "Oh my God." And it was just too funny that someone's mom, people's grandparents have listened in. They're like, "Say hi to my grandparents." So if you want me to say hi to everybody, we give shout outs. But that's too funny. That's too awesome. Well, good stuff. Thank you all for being here. I like that people enjoy this. It's a lot of fun for me too. So, awesome. Well, this has got it. Here, for those who didn't see it, we're going to leave class today with our favorite outro. See everyone later. I'm going to head off to my office.
Hey, Brian, what's up?
Hey, Adam.
Oh, what's this?
Adam, what are you doing? Adam!
No!